All right, can you guys see my screen? Good to go. All right, so I'm just trying to adjust so I can see everyone. Since there are fewer people, I can actually see the squares today. Usually it just minimizes to one square. All right, so today what we're actually going to be talking about is one step above a note, or one step above the t-test that we talked about last week, something called ANOVA, or analysis of variance. So up until this point, we've been talking about, if you have two different measures or two different groups and you want to compare these group means or these measures and see if they're different, how do we test that on a hypothesis under the null hypothesis? So a one-way ANOVA is going to do the exact same thing, but this is going to account for situations where we have more than two groups. So you can imagine maybe even in your own labs and your own experiments, you often have situations where you want to test multiple things. So you might not just have, group A and group B, you might have a placebo, high dose and low dose of a drug, for example. And so you want to see what all the differences are among all of those different groups. And so today we'll talk about one-way ANOVA, which is the way that you would approach that. And so very, very briefly, just to briefly review t-test, remember we have our sort of flow chart. You have just one sample, you're either doing a one sample Z or a one sample T, depending on if you know the population standard deviation. If you don't know the population standard deviation, you're a one sample T. If you have two things that you're trying to compare, if they are two independent groups, that's going to be an independent samples t-test. If they're two repeated measures, it's like a pre-test, post-test situation, that's going to be the paired samples t-test. So what we're going to talk about today is going to be most similar. It's actually the exact same thing as an independent samples t-test. It's just if you have more than two groups. So the thing to keep in mind is this is only going to apply when your groups are fully independent. So you have a placebo group, a low drug dose group, and a high drug dose group, for example. Oh, my PowerPoint just scrolled. Hang on one second. Okay, so in a minute, we'll go into, once I get through all of these slides, we'll show some of these things in R, but you guys remember the GRE test prep or the GRE scores data set that we've been working with. It had a test prep variable. Imagine if you wanted to compare just the no prep versus the prep groups, that would be an independent samples t-test. So only subjects in the no prep group did not participate in the in-class prep group. So you could just compare their scores on their verbal GRE, for example. That's a one independent samples t-test. But if you remember from that data set, we actually had a no prep, an in-class preparation, and as well as an online prep group. So if we actually wanted to compare all three of those to see if there were differences on how each of those groups performed on the GRE, we would not be able to use a t-test because, well, we'll go into why in just a second. But so essentially we need to have a different test for this because of increasing your type 1 error rate. So if we think back to last class, maybe the class before, when we talked about type 1 versus type 2 error rates, you guys remember those? Where if the type 1 error rate is the probability of incorrectly rejecting the null hypothesis, right? So this is saying that you found an effect, but in reality, there actually isn't an effect and you're drawing the wrong conclusion. So if you are going to do multiple t-tests, you're actually going to increase your type 1 error rate. So we have to have a different way to deal with multiple groups. And so an ANOVA is the way that we do this. And so ANOVA stands for analysis of variance, the AN, O, and then the VA. So if you see ANOVA, that's what it is abbreviated for. And so this ANOVA actually stands for a collection of analyses. We're only going to be talking about one of those today. The following lectures will talk about factorial ANOVA as well. And then the next one we'll talk about repeated measures ANOVA. But today we're just talking about a one-way ANOVA for between subjects experiments. And so an example of when we would use a one-way ANOVA would be, okay, we want to examine all three study prep types on, how each of these students did on the GRE when they had no prep, an in-class prep, or an online prep, for example. And so one one way, if you think about it, whenever we have a t-test and we're comparing two different groups, one option could be is we could just do a bunch of different t-tests, right? We could say, okay, I'm going to compare the online group to the no prep group, and then I'm going to compare the no prep group, or the online group to the no prep group, and then I'm going to compare the online group to the in-class group, and then I'm going to compare the in-class to the no prep. So all 1 versus 2, 2 versus 3, and 1 versus 3. However, there's a problem with this because it inflates type 1 error rate. So anytime you have a data set and you do multiple different t-tests like this, or multiple different statistical analyses repeatedly over and over on different aspects of that data set, you are increasing your type 1 error rate. And so this is referred to as the multiple comparisons problem. So whenever you're doing multiple comparisons, so you're comparing this thing to this thing to this thing, or you're doing these two is one comparison, this is one comparison, and this is one comparison, you're increasing your type 1 error rate, because every time you do a comparison, your type 1 error rate exists. So you have a 0.05, we're going to assume a standard alpha, 0.05 chance of committing a type 1 error rate here. You have that same probability here, and you have that same probability here. So essentially, if you do 3 independent samples t-tests on the same data set, but with all these different group combinations, what you actually end up with is a situation like this, where your type 1 error rate is no longer 0.05, it's now 0.14, because this is referred to as your family-wise error rate. And so your family-wise error rate is whatever your probability is of not committing a type 1 error, so 1 minus 0.05, so 0.95, and then exponentiated to however many tests you're going to do. And so if you're doing 3 tests, so 1 minus 0.05 is 0.95, so 0.95 cubed is 0.86, and then your family-wise error rate is obviously 1 minus 0.86. So your probability of making at least one type 1 error among all those tests is 0.14. So now no longer is it a 5% chance of committing a type 1 error, now it's a 14% chance of committing a type 1 error. So why is this a bad thing?
Well, it increases your chance of finding significance when there isn't any, or rejecting the null when you shouldn't.
Exactly. So this is a really bad problem, because you're claiming that you found something when in reality you didn't find something. You're increasing the probability that you're going to do that. And so with 3 t-tests, this is still a pretty small type 1 error rate relatively to how bad this multiple comparisons problem can get, particularly in cognitive neuroscience research. So for example, fMRI research has this as a major problem. That's why there are a lot of very sophisticated analysis techniques for dealing with fMRI data. Because if you think of, if we scan the brain, and I'm not sure how much neuro classes you guys have had yet, but each little data point that you collect in the brain, we break down into a voxel. So it's basically a 3-dimensional pixel. And so you might have, 30 or 40,000 voxels, or 30 or 40,000 pixels in one condition. And if you want to compare all of those to, if you have condition 1 versus condition 2, now all of a sudden your family-wise error rate is going to be 0.95 to the 40,000th power, or 1 minus 0.95 to the 40,000th power. So your type 1 error rate is going to be huge if you do 40,000 t-tests, right? Because every time you're doing a t-test, you're increasing your type 1 error rate. So this multiple comparisons problem can become quite problematic, particularly in the cognitive neuroscience field, because of all the data. So one of the good things is, in neuroscience, we get tons of data from fMRI, but also from EEG, gets tons and tons of data. We collect data on a millisecond basis. So if you can imagine, an experiment runs 30 minutes, however many milliseconds are in 30 minutes, we have, millions of data points. So if you wanted to do a t-test on every single data point that you have, that's problematic for type 1 error. So this is why going into your experiments with a predefined hypothesis is very important, because if you have a predefined hypothesis, you don't have to look at every data point, right? That's not necessary. You would just be doing t-tests for no reason and increasing your type 1 error rate for no reason. So going into your experiments with a predefined hypothesis is one way that neuroscientists deal with this. And then there are other statistical measures that we can take into account where we can do some corrections. And we'll talk about some of these corrections that are more applicable for this type of t-test problem, where you have, 3 to 10 groups that you're trying to compare. We can correct for that in a statistical fashion. Things like, and you actually can correct for it even in fMRI, even up to like 40,000, but it's less common. You tend to see other analysis techniques come in once you're doing, having to do like 40,000 t-tests. You start seeing people sort of narrow down their data set. And this is where you might see like region of interest analyses or time points of interest analyses, things like that. But that's more neuroscience related. That's less about the stats. But this is where this becomes a problem because of this core issue here, where every time you do this t-test on the same data set, you're increasing your type 1 error rate. So if we have 3 groups, we can't really do this. So we can't just do 3 t-tests. And, you can imagine in some other experiments, you might have 4 or 5 groups, depending on all the things that you're wanting to test in your experiment. So one of the solutions to this is to do.
I have a question.
Oh, yeah. Yeah.
Sorry to interrupt. So if your critical value would be like 0.13 right below it, that would be a type 1 error, because that would be technically significant based on the family wise, right? Or my
No, so you're thinking the right way. So one of the ways to correct this is, rather than changing your critical value, so your critical value would still be 1.96, but it's just the actual probability, because you're doing those comparisons separately at 3 separate t-tests. It would be 1.96 the first t-test here, 1.96 on the second t-test, and 1.96 on the third. And cumulatively, that increases your type 1 error rate. But you are thinking the right way, because one of the corrections is to change the threshold by making it more strict. So we can change the threshold and say, okay, instead of a 0.05 threshold, we want to change our threshold to I'll show you the formula in a little bit, but you basically say 0.05 times, or to the third power. So it'd be like 0.0025, I think, is what you eventually would end up changing your threshold to, so that now whatever the critical value associated with that probability becomes the new threshold. So now you have to get an even higher T critical or T observed in order to get significance to correct for that. So that's one of the corrections that we can apply. It's actually the most stringent correction.
Right. So then that 0.14, so what is that showing exactly then? Is it just like what our chances are of having a type 1 error? Is
Yes.
that what it's all?
Yeah. So all this is the probability of committing the type 1 error.
Okay.
So it's not the actual, the
Gotcha.
critical value that you're using, because you're doing these tests independently, is still like 1.96 each time. But whenever you take into account that you've done that, you've pulled from the same data set all of these groups, that means you've actually taken a 0.05 risk 3 times. So that gives you a 0.14 type 1 error rate. All right, a good question. Okay, so an ANOVA is the solution to this. So whenever we're dealing with a one-way ANOVA, which is all we're going to talk about today, this is whenever you have one independent variable, and that independent variable has more than 2 levels. So we can think of our study group. Let's think back to our GRE example, for example. Study type is our independent variable, and the levels are no prep, online prep, or in-class prep. So it has 3 levels. You can also think of this as, if your independent variable is drug, you can have a placebo condition, a drug A or drug B, or low dose or high dose, or something like that. So that's one way, because there's still one independent variable. In the next lecture, we'll talk about a situation where you have 2 independent variables, where we can think of a situation where, let's say you have 2 drugs, drug A and drug B, and then you have a low dose and a high dose of each. So you could have dose and drug would be 2 independent variables, each with 2 levels. So you actually end up with 4 groups, right? That would be a factorial ANOVA, but we're not going to get into that today. Today, we're just dealing with a one-way ANOVA. So you just have one independent variable, and within that one independent variable, you have more than 2 levels. So, and these levels are either nominal, or they can be ordered quantitatively, like low, medium, and high things like that. As long as, but your dependent variable still has to be a continuous measure. So in our GRE example, our dependent variable would be GRE score, verbal, quant, writing, whatever we're measuring. So if we go back, if you think all the way back to the very first class, when I said, most of these tests that we're going to talk about, almost all the tests we talk about in this class, actually, you can break them down into a very simple formula. It's the variance you can explain by your manipulation or by your independent variable divided by the variance you cannot explain. So we're always looking for this ratio. And if you think about t-tests, so think back to what your formula is for an independent samples t-test. We subtract the difference between the two groups, and then you divide by the standard error, right? So the difference between the two groups is the variance you can explain, because that's the difference due to your manipulation. We're dividing by the standard error because that's the error that we expect to see in the sampling distribution, right? The variant, and the other way you can think of that is that's the variance you cannot explain. So we're always dividing what we can explain variance wise divided by the variance we cannot explain. So that formula becomes very important because these are all just going to be iterations off of that formula. And so we can, for a one-way ANOVA, the way that we do this is we calculate the variance among the means and we compare that to the variance within all of the groups. So think about I'm going to stick with the drug example for now because I think that's the one I use throughout the PowerPoint. Let's imagine we have a placebo, a low dose, and a high dose situation. So if you want to look at the variance among the placebo, the low, and the high dose measure, we'll say we're measuring anxiety, for example. We look at the variance among those means. That's the variance we can't explain because our manipulation was the drug, right? So we manipulated something and got different means. That variance we can't explain why those means are different. And then we're going to divide by the variance within each of those groups because we don't know why each of those are different within a group. I don't know why there are different anxiety levels within the low dose group, for example. There might, because individual differences, right? People are different. People just have different anxiety levels. That's variance we can't explain. It's not due to our drug. It exists within the group. So we're always going to be comparing these two things. And so our null hypothesis then is going to be that the variance among that all the groups basically have the same mean and that the among group variance is not going to exceed the within group variance. So as the means get further and further apart, so let's imagine anxiety levels. Let's say we have a placebo group. Let's say our anxiety scores range from a 0 to 100. So we have a placebo group and their anxiety is an 80, a low dose group and their anxiety is, a 60, and a high dose group and their anxiety is a 40, for example. So you have a 80, 60, and 40 group. As those means become further and further apart, that means the difference between our conditions are bigger, right? Because that means our drug is having more and more of an effect. So as those get further and further apart, that ratio is going to get larger because it's the variance between those means divided by the variance within the error variance. So that ratio is going to get larger. So the test statistic is always that ratio. And this test statistic is going to be called an F score instead of a T score. So we've had a Z score before, or a Z observed, we've had a T observed. Now we're going to have an F observed. And so our null hypothesis is that the population variance of group means is 0. The other way that we can say that is that all group means are equal. So that's that group 1 equals group 2 equals group 3. So here's an example of how we might see this. Our alternative, so this is something that's different. Usually our null is that the means are equal. The alternative is that they are not equal. Whenever you have more than one group or more than two groups that you're comparing, the alternative for an ANOVA is that there is at least one difference. Not that they're all different, just that there's at least one. And so ANOVA is what we call an omnibus test. So it tests for an overall difference among groups. It doesn't test for the individual differences. It doesn't tell you which groups are different. We always have to do a follow-up test for this. And we'll talk about these follow-up tests in a second, but basically your sort of process should be do the ANOVA. If the ANOVA is significant, then you proceed to the follow-up test to see where your differences are. If your ANOVA is not significant, you conclude there are no differences among groups. Does that
Would that
make
be a
sense?
post hoc test?
Yes, that's called a post hoc test. And there are tons and tons of different post hoc tests that you can also do, which we'll talk about some of these, depending on if you had a hypothesis going in. If you had a hypothesis going in about which group should be different, then you would do something called plan contrast. If you just want to do all possible tests, there are a variety of these that will do all possible tests and apply a correction for multiple comparisons. And I have a slide later in the PowerPoint that goes through each of these as well. And so there's a bunch of different ways that you can follow up on these. But the first test you want to do is the ANOVA, which is, we also hear this called an F test. And you just want to see, is there a difference? So it's not necessarily that 1 is different than 2, 2 and 3, 1 and 3. It's just that, is there one difference among all these groups that I have? And then you proceed to the follow-up test. Make sense? All right. So the theory of an ANOVA, you also might call this a fixed effects, or see this called a fixed effects model, just as you're reading and whenever you're going through your textbook and stuff. If you use other stats textbooks and you're reading about this, it's also called a fixed effects model. So whenever we're thinking about ANOVA, we are going to want to break down our sources of variation. So if we think about, back to what I was saying earlier, where we know where some of our variability in our data comes from because we manipulated groups, right? So if I just had a drug group and a placebo group, I expect those things to be different, right? Because I put that manipulation into the experiment. So I am expecting variability between those two groups. That's called our between groups variation, and that's the variance we can't explain, right? That's the thing we know should be there because we manipulated that thing, assuming, random sampling and all the other statistical and methodological things were followed. But also within your groups or also in your data, you're going to have other variation. And we often call this within groups variation or residual variation. So both, you might see these terms used interchangeably. And the other word you might see for this is called error variation. So residual, error are always going to mean the same thing. For now, within groups will also always mean that, because we're looking at a one-way ANOVA where we have different groups. So it's always between subjects. So people who are in group 1 are never in group 2 or 3, right? These are completely independent. So that's one of the assumptions for this, is that you have to have independence among your observations. So we have to split up all of our sources of variation, because we know in our data set there are two sources: the source that we know should be there due to our manipulation, and the source that we can't control. There's just error because people are different, right? So there are just individual differences in, we'll say, anxiety levels, and there's individual differences on the time of day someone took your task, or how well they did at your task. There's just error variation in general, and we know that's there, but we're really trying to parse that apart so we can get that ratio. And then once we can look at that ratio, we will compare that F ratio to an F critical value. And if it is sufficiently high, we will reject the null. Just like we compared our T ratio or our T observed to a T critical. And if it was sufficiently extreme and then surpass that cutoff, we reject the null. And so together, your between groups variation and your within groups variation account for all the variability in your data, right? So you have variability within a group in the red here. So this is within the placebo group. These numbers aren't the same. Essentially, this is your within group, and they're not the same in here, and they're not the same in here. That's the error we can't explain, or the variance we can't explain, called within groups. Down here, if we look at the means of each of these groups, notice these are not identical but we didn't expect them to be, right? We did this manipulation. We said, okay, a third of you go to a placebo group, a third go to a low dose, a third go to a high dose. This is the variance we can explain. This is our between groups variability. So we're essentially interested in the ratio of this variability between groups divided by our within groups. Make sense? All right. So are there any questions up to this point? There we go. Okay. All right. And so whenever we get this ratio, that is now going to be our test statistic. So before we were using a Z observed as the test statistic, then we used a T observed as the test statistic. Now we're going to have an F observed. You might also see this just called an F score, or your F value. F ratio is another word for it, but anything with the F. So this is because, just like with the Z distribution and the T distribution, our F score falls on an F distribution. So we're shifting into another distribution again. So we're no longer on the T distribution, now we're on an F distribution. And we'll talk about some of the characteristics of that in a second. But essentially, a F distribution is just the square of the T distribution. So if you took the T distribution and squared it, now you would have an F distribution. So something about the F distribution that you will notice, that we'll get to in a second, is that it's always positive. So your F scores will always be positive. If you ever come up with a negative F score, there's a problem in your calculation somewhere, because F scores are always positive, and F distribution is the square of a T distribution, and the square of any number is always positive, right? So F scores are always positive, and we'll talk about why that is once we get into these calculations.
Well, isn't that because when you square a number, it automatically has to be positive?
Exactly. Yes, it does. But we'll also talk about what, so that's why the distribution is positive, but what makes up that distribution is because we're looking at variances. And think about how we calculate variances. Are variances ever negative? Because they come from what? What is the step before calculating variance?
Sums of squares.
Sums of squares, which is also never negative, right? Because a sum of squares, we square everything and then you sum it. And from that point on, you're not going to have a negative variance. You're never going to have a negative standard deviation. You're never going to have a negative sums of squares. So since we're comparing ratios of variances, you're never going to have a negative F statistic. And because the F distribution is the T distribution squared, and squares are always positive.
Isn't variance like a negative variance would be nonsensical, wouldn't it? Is there?
Exactly, you can't. Yeah, you can't have, if you had a negative variance, there's an error in your calculation because variance comes from sums of squares. And if you've squared everything, and if you squared everything, everything's positive. And from that point on, things stay positive, because after sums of squares, you square everything, then you sum it, then you divide by degrees of freedom, or n-1, then you square root it. At no point can it go negative. Okay, so our one-way test statistic, or one-way ANOVA test statistic, this is our F score, or our F test. We want to get down to this ratio: variance due to treatment, so variance between groups, divided by variance due to error, or residuals, or within group variation. So again, you might see these words used all interchangeably. They're all going to mean the same thing. So one is, you want to sort of mentally separate these things into your variance I can't explain, variance I cannot explain, and we're always looking for this ratio. So the very first thing you're going to do if we want to get this ratio is we're going to go back all the way to sums of squares, and essentially getting all of these variances is just calculating sums of squares in slightly different ways. So we're going to follow the sums of squares logic. We're always going to be calculating the difference of something, you know, the distance between something, squaring it and summing it. But what those things are changes depending on if we want sums of squares between, or sums of squares within, or sums of squares residual. See those interchangeably. So just to sort of visualize this, I'm going to try to zoom this in just a little bit so you guys can see this. Can you guys see those dots there, these little individual dots? Okay. All right, so imagine this is our data set. So imagine we have three groups here. We have a placebo, a low drug, and a high drug, or dose, low dose and high dose. So our placebo are the individual data points in the red, our low dose are in the green, and our high dose are in the blue. So these are how people scored on, we'll say, anxiety. So this line, black line right here, is what we call the grand mean. This is the mean of all of the data, regardless of group. So if I averaged all the red dots, all the green dots, and all the blue dots together, this is the number I would get. So if you see the word grand mean, that means that's all your data averaged together. So that's if you just took your data, put it into a vector, into R and just did a mean statement, and you didn't do, you know, only selecting out the placebo group or the low group, if you just averaged all of it together, that's your grand mean. So if I wanted to get the sums of squares total, if I just wanted the total sums of squares for my whole data set, regardless of group, you would just calculate it as you usually do, right? Sums of squares, you take each data point and you subtract it from the mean, the grand mean, and then you square that value. You do that for each of your data points and you sum that value. That's your sums of squares total. So this is the thing that you've done before with just regular data. Just, you would just be pretending there are no groups. You would just pretend everyone's all in the same group here for your sums of squares total. Sums of squares between groups, or you might often see this called sums of squares model. I also recommend maybe getting like a notes here and saying, writing down all the different words that people use interchangeably for these. So between, model, and variance you can't explain, or treatment, those are all meaning the same thing. Residual, error, and usually within group variance are all the variance you cannot explain. So I'm just trying to keep those straight because different textbooks and different sources, resources use different terminology for it. So sums of squares model, this is the sums of squares between each group. So this is the variability that you can explain, the variance due to your manipulation. So this is going to be the squared distance between each group's mean and the grand mean. So here I have each group's mean in a bar of its respective color, right? So if I took this bar relative to the grand mean, so I subtracted those scores, subtracted this, and subtracted that. And if I squared those and summed them, that's my sums of squares between groups. Because it's each group's mean relative to the grand mean squared and then summed. So it's the identical process here, but instead of dealing with individual data points, we're just doing it with the means. So here you're only doing this 3 times, whereas with your data points, you're doing it what? 1, 2, 3, 4, 6, 7, 8, 9, 10, like 14 times or something, 15. Makes sense? And so that tells you what is the variance I can explain, because this is the difference between your group means and the regular and the total mean. Your sums of squares within, this is the error variance or your error term. You might also see this called. So this is the variance you cannot explain. And this is going to be the square distance between each score and its own group mean. So this is that variability that's happening within a group. So I would take this data point, subtract it from its own mean, square that value. This data point from its mean, square that value. And I would sum all of these, and then I would have a sums of squares within this group. I would have a sums of squares within this group and a sums of squares within this group. And then you sum all of those sums of squares. And that's what gives you your sums of squares error or your sums of squares residual, because it's the variability within a group that you cannot explain. Does that make sense? So what you should end up with, and one way you can check if you're ever doing this, manually, is your sums of squares total should equal your sums of squares between plus your sums of squares within, or residual, because the total is all the variability in your data. All we're doing is partitioning it. We're just separating it into variability we can explain, variability we cannot explain. So are there any questions on this? No?
Well, we would only do those individual things to like understand the concept, but when we're actually running an analysis, right, it would
Yes,
be
so
there for us.
Yeah, so R will do all of these things for you. The only thing, you have to understand the concept in order to calculate an effect size. So you won't actually do these individual calculations, but you will get like a sums of squares metric out, and then you need to know which one to take to calculate effect size. So you have to understand conceptually. And yeah, and maybe like on a quiz or like on an assignment or something. But yeah, like in practice, you're not actually going to be manually calculating this out. But this is what R is going to be doing behind the scenes to partition up your data or your variation. All right, so for the conceptual purposes here, let's imagine we have this data set of anxiety scores. So this is the exact data here. I've just put it in a chart here. So think all the way back to the very first time we talked about sums of squares and standard deviation and variance. Remember, I had these charts. So if I wanted to calculate sums of squares within a group, so remember, this is my error term. So each data point relative to its own mean squared. So I would do this for the placebo group. So here I've got just a little excerpt of how you would do that. If the placebo group mean is 2.2, take 3 minus 2.2, square it, 2 minus 2.2, square it. So you do this for all of these values. Then you sum all the squares, you have 6.8. So 6.8 is the sum of squares for the placebo group within, right? And then if you want the sums of squares within a group for your ANOVA, you have to add up each of these sums of squares. So this gives you a total of 23.6 is your sums of squares error, sums of squares residual, sums of squares within. These all mean the same thing. Whenever we do this in R in a second, instead of going through this manually, doing each score minus the mean squared, summing it for each group, and then summing all that, what we're going to do is just do it for each group. We're going to take the variance and multiply by n minus 1. Because remember, we have a function for variance, and we know that variance times n minus 1 is sums of squares, right? Because we know in order to get to variance, we have to divide by n minus 1. So we already know that. Okay, so that's sums of squares within. So now let's do sums of squares total. So this is all the variability in all of your data set. This would just be the regular way you calculated sums of squares. So each data point relative to now the grand mean. So remember, the grand mean is the total mean in the whole data set, regardless of group. There's that difference. You square it. Do you remember why we can't just sum the differences? Why do we have to square them whenever we're calculating sums of squares?
It would be 0.
It's all, yes, it would be 0, and it will always be 0 because all of the differences relative to the mean are always 0 because the mean is always in the middle, right? Between the mean is the average. Sorry, just knocked over something. Okay, so we always square it and then we sum it. So our sums of squares total 43.73. But again, we could just calculate this doing variance times n minus 1 because we know that this is how you get to sums of squares. So if you wanted to then calculate sums of squares between, so now we have the total and we have the within. So now we're just missing the variance we can't explain, the between groups. We could just subtract our sums of squares total minus our sums of squares within, and this will give you your sums of squares between, because these two always add up to your sums of squares total, because your total is all the variability you have. You're just splitting it up. But if you needed to for, I don't know, an assignment or something, if you just to understand the concept of how to calculate sums of squares between, you take the group means. So the placebo group mean is 2.2 relative to the grand mean. So you get that score, you square it. Oops. You square this. And then you also have to do one extra step here. You have to multiply this times the number of data points that went into that measure. And then you sum those numbers. So you have to take into account how many data points are going into this mean here. But essentially it's the same process, right? We're finding the difference relative to a mean. It's either the grand mean or the group mean, depending on which one you're doing, squaring that number and summing things. The only difference here is that this also takes into account how many data points went into that mean. So essentially here we have 8.3611, you end up with 20.13, which we could have found that out also just by subtracting, because within plus between always equals total. All right, so are there questions about that?
I'm sorry, I came in late, so maybe you went over it. I just wondered, on these different groups, do they have to have the same N, all three groups? Is that a
They don't
rule?
have to. They don't they don't have to. It's nice. So there are corrections that you can apply for this, but it makes it nicer. The math is easier if they do, because otherwise you have to get into like weighting and things because you don't want them contributing differently. Not necessarily at this step, but if you think back to like our sums of squares within, these all have the same group too. And remember, we're just adding these up. So, yeah. But so you can do it with slight, and it depends on also how big your sample size is. So, if you have a situation where you have like an N of 21, or let's say you have like 30, 31, and 32 in your groups, that's not that bad of a problem. Here, if you had 5, 10, and 15, that's a problem, right? Because one group is contributing way more to the data than the other group. And in that situation, you would either need to like parse down one of your datas or collect more data in another group, or you'd have to do something to correct for that. But if you have a big enough sample size and it's just 1 or 2 off, it's not going to contribute as much. So, but
I have an additional question to that. Sorry.
go ahead.
Yeah, I just have an additional question to that. If you do have one set of data of like n equals, let's say 500, and the second set of data of n equals like 5, would you want the 2 set of data to be weighted differently? Like, there's no reason the n equals 5 should be weighted the same as something with an n equals 500.
So what did you say if you had an N of what now?
Like n of, let's say 500 and n of 5, right? Like, you don't want, you said you want them to be weighed the same. Like, I don't feel like it shouldn't be. Okay, got it.
Yeah, you don't want them.
Thank you.
Yeah, you definitely don't want that to be, because you want them to have equal weights and have similar contribution. This is what you want in an ideal experiment.
Yeah.
You don't want
Right.
that. Yeah.
Okay, got it. That makes sense.
And also from an experimental design perspective, you can imagine, if you have one group that has 500 and one that only has 5, then you shouldn't be testing those 2. Like, if that's the only group.
Yeah, you shouldn't be comparing them anyway.
You shouldn't even be comparing those groups either. Yeah, I know. Anyway,
Perfect. Got it. Thank you.
Okay, so, and for all of these going forward, I will always give you equal ends for
Thank you.
ANOVAs and stuff, because the math that you have to do it gets a little more complex. So for all of these purposes, you'll always have equal ends in your groups, and everything will always be balanced.
Perfect.
All right, so another way to sort of think about this, now that we have our sums of squares, just to sort of visually map it out, our sums of squares total, variation of all of our scores, right? So this is difference between each score and the grand mean. And then we're splitting that into sums of squares model, or between groups, or treatment, or whatever you want to call it, and into sums of squares residual, or error, or within groups. And so we've just taken the total amount, split that up, and then we're eventually going to get to a point where we want to take the ratio of model over residual, because we want to see what is that ratio, and is that ratio sufficiently large to reject the null on our F distribution. But there's a problem. So before we can calculate a F score, because eventually, remember, this is the point we're trying to get to, is calculating this F score. And so this table I have set up is called an ANOVA table. You will see this again. I guarantee you will see this again. You'll see this frequently, particularly in the next few lectures, because this table is going to get more complicated once we get into more complicated types of ANOVAs. So for today, it'll just be these 3 rows, but eventually we'll start adding more rows once we get into more complex designs. So you're always going to have a source column, a sums of squares column. Over here, I've got them blanked out right now, but you'll have 2 other columns that we're getting ready to talk about, and then your F score. These 2 other columns are what gets you to your F score. And so the reason that we can't just take a simple ratio here, we can't just say, okay, well, 20.13 divided by 23.6 is, whatever that comes out to, that's our F score. We can't do that because there's a problem with sums of squares. Does anyone remember why we go on to variance? Why don't we just stick with sums of squares all the time?
It gets inflated by the n value?
Exactly. It gets inflated by n. So the more observations you have, the higher your sums of squares always gets. So because we're summing these scores, the more observations we get, the larger our numbers will always get, which then means we're going to be artificially inflating things, right? So remember what we did with variance, we just divided by n minus 1. And remember, another word that we can use for n minus 1 often is degrees of freedom. So really, in order to get from variance, from sums of squares to variance, we divide by degrees of freedom, right? That's exactly what we're going to do here to solve this problem. But instead of calling it variance, we're going to call it mean squares. You might see this abbreviated MS, but it's essentially the same concept. We're going to do this just as a sort of sanity check. We'll do it both for our sums of squares total, we'll do it for our sums of squares model, and for our sums of squares residual. But remember how we calculated each of these sums of squares. Different numbers of observations went into each of these calculations. So let's say we had 15 data points for this example. We had 3 groups, each group has 5 data points. Okay, so we have 15. How many data points went into our sums of squares total? Individual data points that go in. How many times did we do this little chart up here? Let's see if I go back. How many times did we do, how many rows would this have had that we had to go all the way down for sums of squares total?
3
15.
rows,
Enough that-
5 each.
So yeah, so it's 15. So we have 15 data points in sums of squares total. So our degrees of freedom total is going to be 15 minus 1. So that's going to be our first thing. First, that how we'll calculate this first. Then we're going to have to use a different degrees of freedom for model, because we use groups for model, remember? Because we had each group relative to the grand mean. And then we're also going to have to use a different one for within, because we had all of our data points, but we did this 3 times, right? We did
Right,
it.
so we would be subtracting minus 3.
Yeah, it would be 15 minus 3, and this one is going to be 3 minus 1. And the other way that we can always check ourselves is that degrees of freedom total, just like sums of squares total, it's a partitioning. So degrees of freedom total is going to equal degrees of freedom model plus degrees of freedom residual. So we're going to get to this part of the table here. So now we have degrees of freedom model is 2, because we had 3 groups, right, that went into that calculation. So 3 minus 1 is 2. Our degrees of freedom within, well, let's go to total first. Degrees of freedom total, we know we had 15 data points. 15 minus 1 is 14. The easiest way that most people calculate this is just say 14 minus 2, okay, is 12, because these have to add up. 2 plus 12 is 14. But the actual formula for this is take all of your data points, because all your data points went into it. That's 15. And then you have to subtract a degree of freedom for each sums of squares within group that you did. So we did this for placebo, low, and high. So 15 minus 3 is 12. Does that make sense? All right, so now we have our sums of squares and we have our degrees of freedom. And remember, this is, if we want to get to a non-inflated measure outside of sums of squares, we have to divide sums of squares divided by degrees of freedom. And that gives us what we're going to call mean squares, but it's essentially our variance. We're just going to label it mean squares. So now we just divide each of these. And so this is just a summary of this, just in that other format, so you can sort of see. So now we have our next part of our table. So now we have our sums of squares, degrees of freedom, and mean squares. Now I'm not so interested anymore in our total column. This is really just a sanity check. So we don't have to do it for total, because what we're trying to get to is this F score, where we're dividing the model divided by the error. So total actually isn't going to play into this. So we don't have to calculate mean square down here. You can, but you don't have to. So now this 10 is 20.13 divided by 2, because it's sums of squares divided by its respective degrees of freedom. Our MS within, or MS residual, is 23.6 divided by 12, which is 1.97, because sums of squares within divided by degrees of freedom within. Make sense? So each has its sort of respective partitioning. And then finally, we can eventually get to our F score now, because now we have our mean square model and our mean square residual, or the other way we can think about this is the variance that we can explain divided by the variance that we cannot explain. That's going to give us our F score. So down here, all we do is calculate 10 divided by 1.97 or 10.06 divided by 1.97. That gives us our F score of 5.11. Make sense? So whenever we say an F score or F ratio of this variance, you might see this written this way: MS model divided by MS residual, MS between divided by MS within, MS treatment divided by MS error. These are all saying the same thing. The denominator is the error variance that we cannot explain. The numerator is the variability that we can explain due to our manipulation. And then now that we have an F statistic, now this is no different than our regular hypothesis testing. We're going to compare this to an F critical value. So now we're on an F distribution here. We're going to say our F critical value. We will calculate this in R just like we've done with the Z and the T. Remember, we had the Q norm, the QT will now have or P and P norm and PT will now have a QF and a PF function. It'll give you your degrees of freedom or your F critical value. You'll give it your degrees of freedom, just like you do with your T values. Except now you actually have to give it 2 degrees of freedom, because remember, now we have 2. You have your degrees of freedom between, your degrees of freedom within. So now instead of just giving it 1 degree of freedom, you actually have to give it both. And this function comes from, just like with the Z scores and the T scores, these are all just based on tables that people have calculated out, years and years ago before computers existed, or they've calculated out based on this distribution for a given degree of freedom, model and a given degree of freedom residual. What is, and for a given probability in the tail, what is that critical value? Just like it does for the T, but the function just calculates it for you. So what do you notice about this distribution relative to our T and Z distribution that we've had before?
It's skewed.
It's skewed. Yes, it's skewed which way?
Right.
Right. Yeah, so it's always skewed positive because there are no negative values, because the F distribution is the T distribution squared. So it's always just going to be the square of the T distribution. So our values naturally are going to be higher. So remember when we talked about our standard Z score, our typical value, critical value is 1.96, positive and negative. And then when we moved on to T scores, it was usually like positive and negative, 2.2, something like that. It was a little bit higher because we took into account degrees of freedom, depending on our degrees of freedom, of course. And now here you'll see this is 3.89. So now your F scores are going to be your criticals are going to be a little bit higher, because again, it's penalizing you for having however small your sample size is. So you get penalties both for how small your sample size is and the groups, how many groups that you have. And so I mentioned this actually up here. So as your total sample size goes up, your residual is going to decrease and you're going to increase your power, because as your error goes down, power goes up, right? As the levels increase, so as your numbers of groups increases, your model is going to decrease, your MS model number, which is going to then make your ratio smaller. That's going to decrease your power. This is not surprising if you think about this in experimental terms. Which do you think would be easier to find an effect in, comparing 3 groups or comparing 20 groups with the same number of subjects? So you have 5 subject, right? So
20.
yeah, well, it will be easier in the 3 groups because you're penalized because you have 20 groups. So you're splitting the variation across 20 different groups, right?
Oh, okay.
So your power will decrease. And that's given for
Interesting. That's so counterintuitive to what I think. Yeah.
if you're also increasing your sample size, and then you would have it wouldn't have a more powerful effect. But if you're keeping your N constant and your effect size is constant,
Got it. Yeah, that's
yeah, then it's going to go down. And then also your F critical, so that's what this accounts for. So your F critical value is going to be higher for the larger number of groups you have or the smaller sample that you have. And we've seen this before with the T distribution. When you have small sample size, you have a larger T critical value, right? Because you're penalized for having such a small sample. Because when you have a small sample and we're having to estimate the population's parameters, we tend to underestimate the population standard deviation. Because this all goes back to that, you know, how the T distribution is just estimating the population standard deviation to calculate standard error. We're still operating on that same concept. We're still estimating. We're just doing this in a slightly different format now. All right, and so now if we have our F critical value here, if we plotted our F observed on our F critical on the same plot here, we can see that we would still reject the null, right? So our F observed was 5.11, our F critical was 3.89. It's still more extreme, so it still falls in that rejection region.
I have a question, but our degrees of freedom is 12 because we subtracted 3, right?
The degrees of freedom error is 12, but notice here it's degrees of freedom,
Oh,
2, 12. So you have 2 degrees of freedom listed, and
oh,
for ANOVA
okay.
you always will.
Oh, so 12 is the one for the degrees of freedom for error.
Yes, and you always
And
put that 1 second.
okay. And the two is for the 1 is for our because we have 1 between the groups and 1
The-
yeah.
The 2 is the degrees of freedom for between groups, and it's a 2 because we had 3 groups. 3 minus 1 is 2.
Okay, yeah.
So if you had 5 groups, then your degrees of freedom will be 4.
4. Okay. Thank you.
Yep. All right, so questions about this? So do you see how this is very similar to what we've done for t-test? We're just calculating variance in a different way and mean differences in a different way. So with our independent samples t-test, we really were just saying, okay, how different are these means? Let's subtract the 2 means, divide by standard error. And so that, and the standard error represents the error we can't explain. Here, we're taking the difference among all the groups by calculating their variance, by taking sums of squares divided by their degrees of freedom and dividing by the error within the groups. But it's still that same sort of formula of variance we can't explain divided by variance we cannot. So if we wanted to do this in R, so I'm going to go through this in the PowerPoint first, and then we'll jump into R and do it there. So if we wanted to do this in R, you should have, if you've downloaded the template, this data set I've already put into the slide or into the script there. What we would do is this, there are 2 ways to do this. So I'm going to show you both ways. It depends on which package you want to use and how you like to look at the output, but they're going to give you identical outputs. So the first way to do this is by using something called LM or linear model. So this is essentially a regression. So eventually we'll talk about ANOVA is actually just regression, but it's just regression in a table format. So we're just presenting it a different way, but it is just regression. But so we do LM for linear model. This should be familiar to remember when I showed you the formula method for t-tests, and I said we put your dependent variable, the tilde, the independent variable, and that tilde is just the sort of formula symbol that R recognizes, that you're saying, okay, this is my dependent, and I want you to split by these groups. LM always takes this formula method here. So you do your dependent variable, tilde, your independent variable, tell it your data set. And then if you want to see, this will actually give you an output and will give you a p-value. But if you want to see this in the table format, you call this function called ANOVA from the CAR package. We'll go through in just a second. And this will give you this exact table. So notice here, sums of squares, 20.13, residuals, 23.6. So these are the same things that we just found in our ANOVA table. Degrees of freedom, 2 and 12, F value, 5.11, and then it'll also give you a p-value here. And so here's a breakdown of sort of this table, how you can see it. So notice the the sums of squares total and degrees of freedom total aren't listed here. Because those, you don't actually need that information. That's just something if you're calculating it manually and and you're filling in these tables, then you can sort of use a sanity check for it. And so based
Does
on
it
that,
assume
oh, go
a
ahead.
p-value of 0.05?
I'm sorry, say that again. You're breaking up.
Does it assume a p-value of 0.05 is the threshold?
Yes, yes. So the standard threshold is still P of 0.05. So we would still reject the null here. So 0.024 is less than 0.05.
But what if you wanted to like increase threshold or make it smaller, like 0.01?
So if you
How
want
do
to
you-
So if you want to change your threshold, then that's fine. Then if you're saying, okay, my p-value is 0.01, then here you're not change your threshold, but if you wanted to say my critical cutoff value is going to be a p-value of 0.01, then you don't do anything, but you look at this and you say, okay, I failed to reject the null because it didn't reach my threshold, because 0.02 doesn't reach that.
Oh, but you can adjust it like in the function itself.
There may be, I'm not as familiar with the ANOVA output summary. There may be, we can test it whenever we go into R and we'll tab over and look at the help files. There may be a thing where you can actually put in, it might be called prob, P-R-O-B, I think. I'll have to double check on that. But you may be able to check it, but it won't change these numbers. The only thing it will change is what the asterisks that it puts here. So you see here, it puts like 1 asterisk for 0.05, 2 asterisk. Oh, no, it actually won't even change that because, yeah, so maybe if you could go in and change it, maybe it might change this, but it's not going to change the output itself because these are just the numbers. You have to make the decision based on your own criteria, right? So if it changes anything, it would change these codes down here. Like if you wanted 0.01 to be 1 asterisk instead of 2 asterisks, for example. All right, so are there other questions about this? Do you see how we have the exact same values here? And the other thing that you'll notice is missing is the MS column. So we have sums of squares, degrees of freedom. There's no MS, but you can easily calculate that just even based off of these. 20.13 divided by 2 is 10.7 and 23.6 divided by 12 is 1.97, exactly what we got before. And if we divided these out, that would give you 5.11. All right. The other way that we can do this, if you don't do the ANOVA, this function around your LM function, the output for LM looks like this. So it's going to give you a regression-based output. I don't want you guys to worry about this too much right now because we're actually going to cover that in the last 2 lectures of the semester and how to interpret this and how to do regression. But for now, if you are doing it as the linear model and you're not doing any sort of like ANOVA function wrapped around it, it's going to give you something that looks like this with your intercept, standard error, your t values, and then down here it's going to give you your F statistic with your degrees of freedom and your p-value. So if you're still writing this out, you'd still do F. And so this is also, we talked about with the t-value, how you do t parentheses degrees of freedom equals the statistic, comma, p equals your p-value. With F statistics, you do this the exact same way. The only thing is now you have 2 degrees of freedom. You always put DF model, comma, DF error. It's always 212. And then the last way that you can do this is using this other function. This is one of the base R functions called AOV. And you just put brackets around this, and it's going to give you the exact same output as well. All right, so I'm going to hop into R now and actually go through these calculations with you guys. That way you can see it. Let's see if I can find my R window. You guys see my R window? Because I can't. Oh, there it is. Okay, can you guys see this? So if you want to follow along in the R script, it should have the stress data and the GRE scores data. But the first data set that we're actually going to work on is already built in here. So we're going to have placebo, low, high, and I'm just gonna put all these into a data frame called X. So these are the exact numbers that I was using in the PowerPoint. So we already know what the answer should be, right? And so if you wanted to walk through this step by step, if we were doing this manually, the way that we would, just as we did in the PowerPoint, we have to think we're calculating 3 sums of squares, right? We want sums of squares total, sums of squares within, and sums of squares between. So I'm actually going to do total first. I'm going to move this up here. So I'm just going to call this sums of squares total. And again, this is the long form just for conceptual purposes, just so you can see how the math is sort of, so once you guys have the script, then you can sort of play with the math and see how these all relate to one another. So if you take the variance of X, so there's one problem here. If I just take the variance of X this way, look what happens. I get 3 different variances, which is great if I wanted the variance of each individual group. But for sums of squares total, remember, I want all the data points. I don't want to think about the group. So I'm going to do this function in R called stack. This just puts all of your data into a column. So you see how it just puts everything into this column where I have values and, sorry, I'm going to see if I can make this bigger so you guys can see. So stack just puts everything into this column. So I have all of
So
my.
I get a
Sorry, go
I get
ahead.
a warning message that says in bar stack NA is introduced before.
Did you do this bit
I
first?
did.
And it's saying what now?
NA is introduced by portion.
Oh,
Portion.
make sure whenever you do, so do strx and make sure that these are all numbers NUN instead of characters.
So do I just say as numbers or something?
So just do this first, do a strx or for structure.
Yeah, it's numbers.
And then, okay, so there are all 3 numbers. And then if you just do stack X. Oh, wait, did you run the whole thing there, var?
Yes.
Yes, so
Yeah.
that will happen. So notice stack X has 2 columns. So it has the label and it also has the numbers. So we actually just want to grab the first column. So we're just going to grab this first column here. And now this gives us all the data. Yes. And now we can take the variance of all the data. So this is just the total data sets variance among all, regardless of group that someone's in. And then we can, and then we can multiply it by n-1. So our, how many total values do we have? Do you remember? Even if we just look at this.
15.
15. So 15 minus 1 is 14. So we know that's going to give us sums of squares total. So you should come up with 43.73. And then if I want to calculate the sums of squares within a group, so this is my sums of squares error. Remember, this is the variance I cannot explain. So I have to do it within each group and then add all those together. So I'm just going to call this sums of squares within, that's what the W stands for, 1. So this is for the first group. I'm going to get the variance of my placebo and multiply it by however many people are in my placebo group. So notice length of placebo is 5 minus 1, right? Because this is the exact same thing we did right here. But now we're just doing it for the placebo group. Then I could do it again for the low drug group. Except now I'm going to change this to low, change this to low. And make sure you change this to SW or sums of squares 2. And then we'll do it one more time for the third one. And now if I want sums of squares, I'm actually going to call this sums of squares residual, because remember it's sums of squares within, means the same thing. Just so it lines up with the PowerPoint, we're going to do W1 sums of squares within 2, and sums of squares within 3. So remember, this is all, whoops, that's a 2. There we go. Remember, this is all of our sums of squares within our groups, the things that we can't explain. Oh, no, it's not found. That's a problem. There we go. So you should get 23.6 on that. And now, if we want to get, if sums of squares, oh yeah, so that's what I just did here. So adding those together. So now our sums of squares treatment. So the very first thing, this is the between group. So remember, now we need to find what the grand mean is. So do you remember what the grand mean stands for? So I'm gonna call this GM.
Mean of all the points.
Yes, so it's the mean of all the data points. So I'm just going to use that stack function again, so I don't have to split by group. So grand mean, I'm going to get the mean of all my data points. That should give you 3.46. This is just what we found in our PowerPoint. And now remember, we're going to have to take each data point, make each data point's mean, and make that relative to, or each group's mean, sorry, not data point, each group's mean relative to the grand mean. So the first one I'm going to do is the placebo. So mean of the placebo minus the grand mean. I'm going to square that. So this is that sums of squares process, right? Mean relative to the grand mean squared. And then remember, I also have to multiply, this is the weird one, I have to multiply it by the number of data points that are in that group. So we know there are 5 in each group, so I'm just going to multiply that by 5. And then this should, and then we can do this again. I'm just going to drop this down here. This is right, yeah. And then remember, we just do this for each one. But now we're going to do it for low. And then we're going to do it for high. So if I do all of that, we should get 20.13. Sense. So I'm just going to call this sums of squares model. So remember, this is sums of squares between, but we're just going to call it the sums of squares model. And now just to double check, let's do sums of squares total and see, subtract sums of squares residual. And that also equals the same thing, right? Because these add up together. Sorry, I don't know what just happened there. There we go. All right, so that makes sense so far. So now we basically got all 3 of our sums of squares. So now we have, I'm just going to print these out. So this would be how it would be in our table: sums of squares model, sums of squares residual, and sums of squares total, right? This is exactly what we saw in our table: 20.13, 23.6, 43.73. But remember, we have to divide by our degrees of freedom to get to mean square, or really to get to variance, because sums of squares has this problem where the number of observations makes our value get higher and higher because it's a sum. So now we're going to do the same thing. So I'm going to do DF total. I'm going to do DF model, and I'll do DF residual. So remember what DF total was? So it's all of our degrees of freedom. $14, yes. So we want to, someone said that in the chat, wasn't just imagining things. So we want to say, we know we have 15 subjects. So I'm actually going to create a variable here called N with a capital letter. So generally, if you see the capital N, that refers to all of the subjects in the data set, and the lowercase refers to the individual. So you might say N placebo, in low, in high, that would refer to how many data points are in each group. So uppercase N, I'm gonna just call this 15 because we know. So now we're gonna say N minus 1. DF model, remember how we made DF model? We took each mean relative to the grand mean. So we need just how many groups do we have?
3.
3. So we're going to say 3 minus 1. You might often see this in textbooks as K minus 1. Often K is referred to as the number of groups. And then finally, our residual, we could just add up our DF total or subtract DF total and DF model. Oh. Or we could use our formula. We know we have all the subjects. So we have capital N. So we have all 15 of our subjects. And we know we have 3 groups. So we're going to subtract 3. I'm actually going to do this for just continuity purposes. Number of groups, and this is total number of subjects. So usually you would see this K minus 1, and then this is N minus K. All right, and now our last part, we're going to calculate our mean squares. So I'm going to say MS model. Do you remember how we get to these two? We have MS model and MS residual. So of our table, we have sums of squares column filled out. We have the degrees of freedom column filled out. Now we're going to the mean square column. Yes, divide by the degrees of freedom. So we're going to take sums of squares model divided by DF model. And then we're going to do the exact same thing here. Sums of squares residual divided by divided by DF residual. Can I not run that? So now for this numbers, you should have 1.96. Wait, is that right? Yeah, it is. And then 10.06. And now we're to our F observed, just like we were to T observed last time. And all this is where we're getting that ratio. Variability I can't explain divided by variability I cannot explain. So MS model, I can't explain that. That's due to my manipulation. That's due to the difference between drugs, placebo, low and high. I can't explain the MS residual. I don't know why those people are different within the groups, just due to error. So now we have an F observed, 5.11, just like we saw in the PowerPoint. And now F critical, I'll call this F crit. Now instead of Q norm and QT, now we have QF. And then we're going to give it our probability that we want. So 0.95. And then do you see how this pops up? P comma DF1, DF2. DF1 is always your DF model. DF2 is always your DF residual. So it's always going to be in that order. So we can go ahead and put DF model, DF residual. And now we can see that this is 3.88 or 3.89. I rounded up in the PowerPoint. And then we can also, if we still want to report the p-value, which we almost always want to do that, we do PF instead of P norm or PT. Now it's PF. So again, now we have our Q, which is F observed. DF1 and DF2, same thing. DF residual. And now this gives us the exact, oh no. That's not, hang on. I have to do the lower dovetail. Oh, false. And off it today. Yes, for SS total, I will send that. Here, I'll send this. I'll actually just grab this whole chunk here, all the way down to here. So this is the whole conceptual part of creating that ANOVA table. And you can see here, our p-value is 0.0246, exactly what we saw in the PowerPoint. And if we wanted to plot this, just like the way that I created the plot in the PowerPoint, I just made the plot, I just made the F distribution here. And then I plotted a line for our F critical. You can see that I called F crit here. And then F observed. So I plotted a black line for F critical and a red line for F observed. And you can also, you know, from our plotting, we know that you can add in text. So I just added in this text to show where our degrees of freedom are F critical, and we can see that this is more extreme. So we reject the null. At least one difference among groups. Make sense? So this is all exactly what we did in the PowerPoint. This is just the R code to do it. Again, you're not in practice. You will not be doing this other than like outside of assignments and exams for, you know, class purposes. You're not going to have to be calculating out sums of squares and things like that unless you're doing something very specific or very odd in actual research, because we have functions that'll handle all of these things for us. And so the functions that we went through, I'm going to start with the base R one, AOV. This is going to give us, oh, I guess, yeah. Maybe I need to do this first. So I'm going to stack the data how we were stacking it earlier. So almost all of these functions require the formula input. So you're going to need the data stacked. So I'm going to do all. And then
Is the lower T equals true the default for that?
Fault, lower tail is fault. Yeah, lower tail is true as the default. So we need lower tail as false, because otherwise it gives us, it looks on this end and we're not interested in that end. We want to see the tail, right? All right. Questions about that? I guess also the other thing is if, yeah, because your F observed goes in here. Yeah. Okay, so you can see the stack gives us, it stacks all of our values. Stack automatically gives your variables these names. These are the names that it just calls them, values, and then here IND for, I'm guessing independent, because I don't think, what was our usual value? Yeah, so this is the default values and then IND. So I'm just going to rename that to, oh, apparently this was sleep instead of anxiety. I'm going to change it. Well, we'll just leave it at sleep. Okay, so pretend this was sleep instead of anxiety, as I've been talking about all class. So we can see here, now we have our first variables named sleep. So number of hours people are sleeping. And here's the dose of the whatever medication that they got. All right, so very first thing, if we want to use, this is the base R function for ANOVA, it's called AOV. The very first thing that we're going to do is make our independent variable a factor. So this just makes it more readable for whenever it outputs, it'll give it all the labels and everything. So we're going to say X, oh no, this is all dose. So a dose is our independent variable with 3 levels here. And then we're going to say as factor all dose. So this should work here. Yeah, so now you can see we have a factor here. Placebo, low, high. And now we're going to create the model. Here, AOV. So our formula is going to be sleep. So you always want your dependent first, your tilde, and then dose, and then you can specify your data set here. Alternatively, you can also do all $sleep tilde all $dose, and then you don't have to put this in. You don't have to input this. Does the exact same thing. And now when we do this, we can see here, we have the exact same output, degrees of freedom, 2 and 12, our residuals, And then our, let's see, where is our, oh, I think I have to do summary. So this will not give you the p-value. You have to do summary first. So we're going to create this into, I'll call this ANOVA AOV, since this is the AOV function we're using. And then if you do summary, ANOVA AOV, so we're just passing this object. So we've just made this an object and then we're passing it to this. This will give you the ANOVA table that you're used to seeing. And you can always do this all in one line. So you don't have to make this into an object right here. You can actually just grab this AOV. I'm going to copy and paste this down and just do summary parentheses and paste that whole thing in there. And it does the exact same thing. So you don't have to make it into an object. You can see over here, it's just a list and it has all the information from the ANOVA function in that list. So residuals, values, contrast, all that stuff, which we'll talk about contrast in a second. All right, questions about that? And you see, this gives us the exact same values. So this is the first way, that this is the base R way. There's also the CAR library that you can use this ANOVA function right here. So if you don't already have the CAR library installed, do install.packages for CAR. I'm not going to do that so it doesn't update. So if you use LM, we'll call this ANOVA LM, do LM, and you're going to do the exact same thing. Sleep tilde dose data equals all. So again, this formula method. And now if we do ANOVA LM, you can see it gives you the exact same output. If you just do the LM function here, it gives you the regression based output. So it gives you like the intercepts and everything. Oh, it's summary. I always forget the summary statement every time. Yeah, so this will give you the regression based output here where you have your parameter estimates, standard error, t-values, p-values, intercept, your R squared, all of that. I don't want you guys to worry about any of this right now until we talk about regression. If you just do the summary for LM, it really, you're just looking down here. F statistic, degrees of freedom, p-value. And all this again is highlighted in the PowerPoint. All right, so are there questions about that? No? Okay, so I think, let me see one last thing. Yeah, okay, so so I think what we're gonna do is take, if you get, since we have a few people here, or do you guys want a break, like a 5-minute break, or do you want me to just keep pushing through? You feel like you need a refresher or like a?
I don't need a break, so yeah.
If you guys don't need a break, I'm just gonna, okay, you keep going. If you guys are good, then I'm good. So we'll just keep pushing through and then we can maybe get through it 10 minutes early or so. All right, so the next thing that we're going to talk about is effect size. So I'm going to hop back into the PowerPoint because just like with t-test, we have effect size. Oh, I guess you guys need to see that. There you go. So just like with t-test, we have effect size. We always use Cohen's-d. With ANOVA, we're going to start branching out to some other kinds of metrics. One kind of metric for effect size in ANOVA is something called R squared. And so you probably saw that come up with the regression based output. R squared is actually also a effect size metric for a t-test as well. It's an alternative to Cohen's-d. R squared is this, that's more in the regression world, but essentially R squared gives you your proportion of variability accounted for. So it, I think our R squared on the last, on the, this example here, you'll see this was 0.4604. all this means is our model is accounting for 46% of the variability in the data. So that means our groups account for 46% of the variability. So the R squared metric is really just saying, okay, this is our variance we can't explain divided by the total variance that we have. And you can also calculate R squared for a t-test as well. So we just didn't talk about it, but there is there's a conversion from a t-value. If you have the degrees of freedom, which you should, if you're doing a t-test, then you can calculate what the what the R squared value is for a t-test as well. And so this applies for ANOVA as well as a regression when we get to that. So regression also, or whenever we were talking about ANOVA, we often call R squared. You might often see this called eta squared. There's also another metric called omega squared. And so these are just two different measures for estimating the proportion of variance that we can be accounted for by our factor. And so eta squared here is equal to R squared. It's the Greek symbol or letter eta. And this is only the sums of squares model divided by the sums of squares total, which makes perfect sense if we think about this is just telling us the amount of variance we're explaining. It's just the variance we can't explain divided by how much variance there was, right? So that makes sense. It is slightly biased, however, because we're dealing with a sample, we're estimating population parameters. So again, we're going to overestimate the true effect. So this is always a problem whenever we're dealing with samples, which is also an even worse problem whenever your sample size is smaller, just like what we talked about in t-test. So a better estimate is omega squared. So this will directly take your error variance into account. And so you have all these metrics here from your ANOVA table, right? So you have your sums of square model, subtracting out your degrees of freedom model times your mean square error divided by sums of square total plus mean square error. And so all of this information is in there called omega squared, but there's also built-in R functions that will calculate this for you. But essentially your output of your F table will also give you all of this information if you have to manually calculate it. Or if you want to manually calculate it and test if the function is correct. So we'll go through how to do that in a second after we talk about the follow-up test. And so we'll sort of do that whole chunk in R as well. Okay, so we have a significant F test. Yay. So one thing I do want to mention, I think I mentioned it with t-test, you know, when you're writing up those results, you say, we found a significant effect, comma, then you state your T statistic, right? You say T parentheses degrees of freedom equals your T stat, comma, P equals your P value. With an F test, you do the same thing. You say, okay, our results showed a significant ANOVA or significant one-way ANOVA, comma, F, and then you have to remember you have 2 degrees of freedom. So you would write it out like this. F 212 equals 5.12, P equals 0.0, whatever. But then for an F test, you always have to have a follow-up statement after that, because it's not enough just to say, okay, we found a significant F value. That's it. You have to say we found a significant F value. That just means at least one of those groups were different. We need to figure out which groups are where the differences lie. And so these are your post hoc tests that you'll do, or post hoc meaning follow-up tests. And this depends, which test you do, depends on if you went into your experiment with very clear hypotheses about which group should be different than which, or if you are doing exploratory analyses and just want to test all groups, or if your hypotheses think that all groups will be different, or if you aren't interested in certain comparisons. So it just depends on your experiment, basically. And it also depends on how many groups you have, because remember, with these follow-up tests, we're essentially going to be doing some type of t-test specifically comparing groups, or some variation of a t-test comparing groups, and then applying a correction for either multiple comparisons, or if you're, and that's for the follow-up test when you don't have a priori hypotheses. If you have a priori hypotheses, it is still like a t-test, but there is less of a penalty, essentially, because you're doing fewer tests. But so you have to think these things through about, it's very experiment specific. So essentially we get your significant F value, you find your R square or your R squared, eta squared, your effect size. And remember, this is just the effect size of the F test overall, not of any individual comparison. And so then you decide which kind of tests that you're going to do. I mean, I guess technically you make that decision before you do the analysis, because if you had planned hypothesis, you would already go in with planned contrast. So the first type we'll talk about are generally called post hoc tests. They're generally not planned in that you don't have any clear hypothesis. Let's say you just want to test all possible groups. So you want to see if group 1 is different than 2, 2 and 3, 1 and 3. All of these are just going to be t-tests that are comparing means, and they're applying different multiple comparisons corrections. So remember, we talked about multiple comparisons is a problem. It inflates type 1 error rate. So all of these different post hoc tests are just different ways to correct for that. They range from super, super strict to really not strict at all, where there are only very few situations where you can use them because they don't do any correction. So one of the most common, and I briefly mentioned this at the beginning of class when we talked about multiple comparisons, is the Bonferroni test. And so your Bonferroni correction is the strictest multiple comparison correction, because it essentially takes however many tests that you're doing and then calculates a new threshold for what you can call significant. So this is called your Bonferroni alpha or your family-wise alpha. And so this will tell you, okay, if your standard alpha is 0.05 and you're doing 3 tests in our example, then you say A minus or alpha 0.05 divided by 3. Now this is your new value for what is deemed significant to control the family-wise error rate. This is by far the strictest, and most of the time, unless you have like 3 or 4 comparisons, most of the time you're not going to use this because it's so strict that it really disables you from finding a significant effect. So using a Bonferroni correction increases the likelihood that you're going to commit what kind of error if it's too strict.
Type 2.
Type 2 error, yes, because it's going to increase the chances that you're going to miss an actual effect because it is very, very strict. Sometimes this is what people do, and that's fine, but often you very rarely see this used in practice. Particularly, like I was mentioning at the beginning of class, if you have fMRI or EEG data where you have, especially the fMRI data, where you're having like, hundreds of thousands, if you want to test every single voxel, you would never find significance because your Bonferroni alpha would be so tiny that you would never actually be able to reject the null. But this is by far the simplest calculation because it doesn't actually change the test you do. It just changes the threshold for what you deem significant or not. Then, so one way that you do this in R, and you can apply all these different tests, which I'll go through what each of these different tests are in just a second, is by doing this pairwise.t-test function. This will be set up just like a t-test for each of the groups that you want to test. And then it will have an option at the end called p.adjust, where you can put in which method that you want to adjust the multiple comparisons, or what method you want to use to adjust for multiple comparisons. And it will do that calculation for you and spit out an adjusted p-value. And so the Bonferroni, if you want to use the Bonferroni method, this is how you would do this. Less conservative corrections are the Holm, Hochberg, Hamel, and Benjamin Hochberg. This often you just hear this called FDR, or false discovery rate. That is one of the most frequently ones I usually use is false discovery rate, or Tukey's is another good post hoc test that will automatically correct for multiple comparisons. Tukey's is really good if you have a lot of groups, because if you imagine if we have 3 groups, we're doing 3 post hoc tests, right? 1 to 2, 2 to 3, 3 to 4. But imagine if you had 6 groups. Now you have to do 1 to 6, 1 to 5, 1 to 4, all the way. So it's basically 6 factorial, right? So you're having to do a lot of, or I guess not 6 factorial. Oh yeah. No, it's not 6 factorial, but you're having to do 10 tests, I think. 6. Yeah, I think it's like 10 tests. Sorry, I can't do that math in my head. But if you're doing 10 tests, you can imagine Bonferroni is going to be very, very strict. Tukey's is often good for this. HSD stands for honestly significant difference. So Tukey's HSD. Duns, this is just another word for the Bonferroni. So if you put in Duns, this is essentially, actually, if you want the Duns, then this is going, you have to put in Bonferroni as the keyword here. Fisher's LSD, this, you can only use this one if you have 3 groups, because Fisher's LSD actually doesn't actually change really your, it's called Fisher's least significant difference, and it doesn't actually correct beyond 3 groups. So you can't really use that if you have, so it's very liberal. It's the most liberal one, but it's so liberal that you can't use it if you have more than 3 groups and you're doing more than 3 comparisons. Then you have Newman Kuhls and Sheffe. I have a chart down here, or a sort of blurb about each of these, because it's honestly hard for me to keep all these different tests straight. And I've been doing this for years. I usually just end up looking up at the help files to see if I need like a different test. But most of the time I'm using FDR, so false discovery rate, or the Tukey's HSD for most cases. All right, and so here's all of these. I would just recommend keeping this just as a resource, you know, for yourself and for your own research, if you need to look into different multiple comparisons tests. But yeah, so Tukey's is really good for greater than 6 groups because it is really good at correcting when you have a lot of comparisons that you're going through. All right, so whenever you have, if you have any doubts about your underlying assumptions of your ANOVA, which by the way, these are very, very similar to the type 1 or independent samples t-test, where you need independence, homogeneity of variance, normality, all of those things that we talked about. These are going to be the same thing for a one-way ANOVA. If you're nervous that you violated some of those assumptions, then always default to a more robust post hoc method. If you don't have hypotheses going in, default to a more robust post hoc method, because you don't want to be unclear on your like waving on your assumptions and, you know, not sure if your F-test is really even reliable, and then using a very liberal post hoc test also. So you're going to set yourself up for committing a type 1 error, basically. So if you're like, oh, my data is like not so great, I violated a couple assumptions, then definitely don't use Fisher's LSD if you've already got problematic data, because that's going to be the most liberal one. So you don't want to do that. Default to a more strict post hoc test to sort of account for, you know, some of your other issues. All right. So this is just going through the different post hoc tests and what you'll sort of see in R whenever we do this. So whenever you put in the pairwise t-test, you'll notice that we're going to set this up very similar to the t-test that we've done before, t.test. We just put pairwise in front of it. Oops. So you put your dependent variable, independent variable, and then here's this argument that where you can specify what type of correction you want to do, p.adjust.method, and then you specify one of these words. I always get these terms mixed up for the different, because it has to be the exact word that R wants, right? If you type in Bonferroni with a capital B, it's going to give you an error because it's not looking, it has to be that exact word. So I always use the help files on these to go and look at what the keywords are most of the time, because I can never remember what each one is, because in a different function, instead of Bonferroni or instead of like Tukey's, for example, you don't put in Tukey's, you put in HSD, which, so like I can never remember these things. So I always just look at the help files to know which term to put in here.
And a question.
Yeah.
So we would have to basically do an ANOVA and then a post hoc test, which would be a follow-up test, which would be a pairwise t-test, not the independent t-test though.
Exactly. Yes. If you're doing the ANOVA and it's significant, then, and if you're wanting to do all possible comparisons, if you're only, let's say that you had 6 groups and you only actually were interested in 3 of those comparisons, then you don't have to do this post hoc work. That will be plan contrast, which we'll talk about in a second. But if you want to do all possible comparisons, it's ANOVA, then post hoc, which are these pairwise t-tests. And so these pairwise t-tests, unlike the output of t-dot tests, remember t-dot test gives you the confidence intervals, the estimated mean, the degrees of freedom, the t-value. The p-value gives you that whole little blurb of information about one t-test. Pairwise t-test gives you this p-value table for all comparisons for all of your groups. And so here you can see, here's the p-value for low dose compared to placebo, high dose compared to placebo, and high dose compared to low dose right here. So it's not going to give you t-values and degrees of freedom. So in that, it is still doing a t-test, but in that sense, it's not going to give you all of those, that information from the t-test. It's really just going to give you the p-values because that's all you're interested in. Your primary analysis was an ANOVA. These are the follow-up tests. And so whenever you're writing these up, you would say, you know, had a significant F test, put in your all your F test statistics. And then your next sentence might be, if this is what you did, you might say, we did a follow-up post-hoc pairwise t-test, Bonferroni corrected, and found that low dose was, you know, higher, like, let's see, what is it? That low and high, that high dose was significantly different than placebo and low dose, but low dose was not different than placebo. And then at each of those statements, you would just put in a parentheses P and give it the p-value supporting that. So you don't actually have to put in the whole T statistic for these pairwise follow-ups. And I'm sure if you guys are reading articles, you'll probably see that whenever people do pairwise tests as follow-ups, they're just putting in the p-values because we've already done the main test, which is the F test. Often you also report mean, standard deviations, things like that.
Allison, they're giving us the p-values in E.
This is
Love-
scientific notation. So if you,
Very.
our defaults to that, if you don't want it to, then whenever you first open it up,
Oh,
type in
that's-
that option SciPen, and then it will not do it. But essentially that's like 0.00000000036. So a very small number. But yeah, it's doing it in scientific notation. All right, and and I will point this out in a second, but in just a minute, whenever we do this, you can also put in, I don't recommend it, but you can also put in none here, and it will not do any correction, but just for conceptual purposes, we'll do it in just a minute. And you'll see that this low versus placebo, this is P is 0.09 when it's corrected, but when it's uncorrected, it's actually significant. So you'll see that what the corrections are doing. And that's also a good way to show yourself sort of which are the stricter corrective methods and stuff by just testing and, you know, changing these, looking at the different ones. But you also should make those decisions based on your situation, based on all of these notes here. All right, so here I actually have it in here. So the none, you can see here, placebo and low dose, you can see this p-value actually was quite significant, right? It's very, very small. And our Bonferroni correction corrected it to 0.094. But remember, Bonferroni is the most strict correction. So if we did an FDR correction, this would probably still be significant because FDR isn't as strict as Bonferroni. I think I have that. Oh, maybe not. Maybe I don't have that one here. And then another one that we can do is that I commonly use is Tukey's honestly significant difference, or Tukey's HSD. However, one downside, you cannot use this in pairwise t-test here. So Tukey's has its own multiple comparisons. You have to use this post hoc library from this desk tools. So if you'll remember back, we actually used this when we were testing assumptions. So if you're testing assumptions with like the, I believe it's the Shapiro-Wilks test and some of the Welch's test stuff for the t-test. This also comes with a function that does this Tukey's post hoc test here. And so here you can see the output of this Tukey's is going to be, again, less conservative than Bonferroni, but it's not going to be as powerful as Holmes. So there are all these drawbacks, you know, but these are all going to be very like situation specific to your experiment. And what I've often found just from honest experience is different labs have different standards that they just tend to do. So PIs tend to have preferences, and I'll say, well, I always use this one. And that's generally what you'll probably end up doing. It's just what the test, because there are so many, there are pros and cons to every test. It just depends on who you're working for, basically, and what their sort of theory on multiple comparisons, corrections, and all these tests are.
You would
Um,
never use the none for the pairwise comparison, right? Like in a
No.
realistic setting.
No, so yeah, so you would never use the none because you always need to be correcting for those. The only time, if you have technically a Fisher's LSD, if you have three comparisons or three groups or fewer, you are using the none because that's what the Fisher's LSD is doing. But you, at that point, you could just do the t-test yourself because there is no correction being applied. Yes. All right. Okay. So here we have, okay, so we have our post-hoc test. Again, think about these in terms of you either don't have a hypothesis going in or you want to test all possible comparisons. So maybe you do have a hypothesis, but your hypothesis is that there are going to be differences among all groups. That's when you're going to do those follow-up post-hoc tests because they are going to correct for every possible difference. The alternative is to do planned contrast. So if you go in and let's say that you have a situation like this, our drug example, where we have a placebo, a low, and a high, you can go in already with hypotheses about what's going to happen, right? So maybe, and that's all going to be dependent on your lit review and, you know, all of the literature that you've been reading and your sort of hypothesis going in. But that can save you test because you don't necessarily have to test all possible conditions. So in a 3-group example, that's not very convincing because doing 3 tests the corrections aren't that harsh because you're only doing 3 tests. But if you get up to a situation where, you know, if you have a bunch of factors and you have a bunch of different interactions where you're ending up testing, you know, 6, 7 groups, maybe you're actually not even hypothesizing that group 1 will have any effects with group 6. Then if you still do those post hoc follow-up tests where you're doing all possible pairs, you're just increasing your type 1 error rate and then correcting for that increase for no reason. And that correction is going to apply to all your tests. So whenever you're having to test all possible comparisons, you're just making it more difficult to find a significant finding if you didn't need to be doing that test to begin with, if that makes sense. So if you can have planned hypotheses going in, particularly when you have a lot of different groups that you're wanting to test, this is ideal because then you can say, okay, well, when I collected this data, I actually only wanted to test group 1 and 4 and groups 2 and 6, for example. And so then you can actually do your planned contrast where you're just doing those tests and now your multiple comparisons correction is way less strict. So it's going to be way less harsh. All right, and so the basic idea of doing these planned contrast is that we're going to further break down the variability of testing specific hypotheses. And so you can sort of think about when we did our ANOVA, we're breaking down that variability on the whole, just all of our groups, all of the differences relative to all of the error within all of the groups. But we can further partition that error or that variance and see if we can parse down into that and see if there are specific differences. And so contrast weighting is not necessarily intuitive for a lot of students. So you have to sort of think about if you've ever done dummy coding for variables where you're basically assigning like dummy values to give them different weights. That's basically what we're doing here. And so there are a few rules whenever you think about contrast weighting. So your contrast must be independent. They cannot share information. So they must test unique hypotheses. Otherwise, you're back to your post hoc tests, right? So you're back, if you're testing all possible pairs, then you're back to your post hoc test. So each contrast should only compare 2 chunks of variation at a time. And then once a group has been singled out, it cannot appear in another contrast. This is because they must be independent, right? So you can't be testing group 1 with group 3 and then in a separate contrast test group 1 with group 4. So typically the way we think about contrast is a sort of drill down effect. And so these are really good whenever you have very clear control conditions, or very clear, drug, no drug, or low, medium, high conditions, sort of like that. So I think a picture is actually a better way to show this down here. So imagine you have your variance that you can explain by the model. So this is that sums of squares model, right? So this is what we know. There is a difference among one of our groups. We don't know which one. So we can, for our plane contrast, something logical that would make sense is to compare, okay, drug versus no drug. So we would compare the placebo versus the average of, or the collapsed average of the low and the high dose together. And that's one contrast. And then let's say that, we find something significant between those two groups. Then let's say we have a second hypothesis that not only will there be a difference between no drug and drug, but we also think the levels of the drug matter. So then we say, okay, we can drill down even further within the drug collapse category and directly compare low dose and high dose. And here now we've only done 2 tests, right? Does that sort of make sense? And so we've never actually used, since we use placebo here by itself, we singled it out. We can't use it again in another contrast because it has to be independent, but these we collapse together. So now we can further split these down. So think of it as sort of like a drill down method. Any questions about that?
I just was like, if you had something where the low dose you expected to have, that doesn't make sense. So I guess less of an effect than the placebo, and the high dose to have more of an effect than the placebo, then you wouldn't set that up. But I think I'm saying something stupid anyway.
No, so in that, not that you're saying something stupid, but in that situation, because you wouldn't expect that, this experiment is very much set up for plane comparisons, because that wouldn't make sense to think, okay, well, the low dose is going to be different than this one, but because of what those variables are. But there are experiments where you don't actually have that clear distinction. And that's when I would probably default back to post hoc tests by testing all possible pairings, because that situation is where a post hoc test would be very helpful, because I can look at low dose to placebo, placebo to high, low to high, right?
Yeah, you just didn't want to in some way average away the results that you actually got. That's what I was trying to figure out. But anyway, yeah.
Yes.
Okay.
Yes, and that is a concern, right? That by looking at it this way, that maybe you are averaging out results, but that would only happen if the low dose was so much lower than the placebo. And so in this type of leveled study, then it wouldn't make more like lit review theoretical sense, I guess.
Thank you.
So I'm just so the difference between this and a post hoc would be that you would have to, or you would make less corrections, right? Because you're only looking at, so is that the only difference? Because I'm having trouble seeing like what difference is this? Like you're just not comparing, control versus the drug, between the two drugs. But that's like the only difference, aside from like also not adding more corrections.
Yes, but the way that the model will correct, because this will all be done in a regression-based method. So the way the corrections are added is they're actually modeled based on dummy coded variables. So mathematically, I can explain it better once we have a better like foundation for regression, but basically it's going to model these different contrasts based. It's like it's doing a t-test, but the corrections are less harsh. So it's not doing as many, but also they're less harsh because of the way that it's doing these, because they're not just straight out t-tests. It's like putting it all into the model. So whenever you'll see in R in a second, we're actually going to assign the contrast before we even do the LM statement. So we'll do the LM statement that we were doing to do the ANOVA, and it's going to spit out the ANOVA plus the contrast all together. So it's not actually 2 separate steps. It's all one step. It's all going to do the testing of the model together.
But can't you assume that if there's a significant difference between the high and the low dose, there has to be a difference between the high and the control at least? Right?
Maybe, yeah. So if there is a difference between the high and the low,
there has to be between the high
should
and the
be
control.
in the high, unless the placebo is not working. The placebo effect is very strong. right? But if that was happening, then I would say, because that doesn't make sense, that's a red flag for a type 1 error, right? Because it's so unintuitive, right?
Well, I'm also thinking, and like, because I work with animals now with humans, I think, I mean, I don't know, but clearly in humans, the placebo effect is stronger than in animals, I want to say. So I'm not even thinking about, I guess, in humans. So maybe that's why I'm thinking like that,
But yeah, so if you had a stronger placebo, if your a placebo effect was so strong that then it wouldn't be different than high. Yeah, yeah, and then at that point, if you still had a high versus low difference, then I would say, then like just from a logical perspective in that setup, I would say that's probably a red flag for a type 1 error, because that doesn't make sense from that experimental design. But there, I mean, even so, the placebo being that stronger, if it's not different than the high dose, or I mean, I don't know, maybe there could be situations, because you do see sometimes dose response curves, right? Where, like, let's say a low dose is actually better than a high dose, because you can overdose. So I guess there could be a situation where there's like an inverse U. So I don't do
the
drug
cooling
research.
effect.
Yeah,
well.
so like I don't do drug research, but I always think of it as like, so I used to do attention research, and attention and arousal is this way. So if you're under aroused, you perform really poorly, and if you're over aroused, you perform really poorly. But if there's like a midpoint of arousal where your performance is good. So let's say if your dose is medium and high, you could actually get an effect where the medium is more effective than the high, and the high equals the placebo. But I don't know what that would be in the drug world, because I'm not a drug researcher. But in the attention world, you could definitely have something like that. Yes, so, but just as a full disclosure, I almost never do these plain contrasts, because most of the time, if you have very elegant design, if you have a good enough design where you sort of drilled down into your construct and you're not testing like thousands of conditions a lot, like if you're, got it down to like 3 to 5 conditions that you're testing, a lot of times I actually just do these post hocs and just see all possible comparisons, because I actually have found, particularly in cognitive stuff where, we're still figuring things out, and some of these effects are really small and like they're nuanced things, that you find things that you don't expect. So that's the downside. If you do these contrasts, you're never actually testing high versus placebo, right? Or low versus placebo. You're testing the average of these two. And so you have to really go in with a very clear hypothesis of what you think is going to happen, and that's what you test. So from a statistical perspective, this is good. From a research perspective, I tend to err on the doing all possible comparisons, because I think that's where you find the interesting effects. Like as a scientist, that's what I err on. But again, it's a balance, because you don't want to over restrict yourself and not find anything, right? Because you've done so many multiple comparisons, corrections, or so many t-tests. Yes, so all good things to think about. It's always, I guess, a balance. But here you can see other examples. So and these plain contrasts tend to work out best when you have a clear control group. And so a lot of times, even if we have like a control group, it's in cognitive stuff, I feel like often we're testing very different things where it's not so clear what we have a control condition, I guess, but it's less leveled like this. Like we don't necessarily have a low, medium, and high frequently. Like they're different levels, but they're not necessarily ranked. And so sometimes some of these don't make as much sense. But here you can see, let's say you had 3 or 4 total groups. So a control, experimental 1, experimental 2, and experimental 3. Then you could partition it this way, where you do contrast 1, contrast 2, and then contrast 3, in whichever way made logical sense for your experiment. And now, instead of having to do, all possible pairwise comparisons, now you're actually only doing 3 contrasts.
I'm a little bit confused. So if you did this comparison, and let's say you would have otherwise found a statistical difference with just one group, so just E1, but the other 2 no. Would you find that doing this whole group E1, E2, E3 against control?
E1, if you would have found the difference E1 versus control.
Yeah, but not with E2 or E3 versus control.
That's it depends on how strong that effect is, because this is going to, the control is being compared against the average of these.
Okay,
Yeah, so if you had a specific hypothesis that E1 would, and you needed to test that specific thing, then either you would need to just only be testing E1 versus a control group as your follow-up. And then you don't have to do any multiple comparisons, because that's just your only follow-up. Or I would again suggest going back to these two post hoc all possible comparisons tests, because if you actually
Okay.
want to see the different contributions relative to the control, which again, that's usually in the science, all the stuff that I've done, that's always what I've been interested in, is how are things changing relative to a control. So often I actually don't even have a control condition most of the time in the things I do, because I would subtract all of my variables from the control. So then everything is a difference relative to control, right? So like if I had if I had level 1, 2, and 3, I would take all those variables and like subtract the control out. So I could have like for some things that I used to do. So I would have like everything was how did it change relative to the control? And then I would do a one-way test among those 3 different scores.
okay,
But
great. Thank you.
Yeah, but that's irrelevant for what we're talking about here. But yes, if you want to specifically compare like E1 to control, E2 to control, things like that, then you're either gonna have to do all of those post hocs that way, where you do all possible comparisons, or something like what I'm mentioning, where you create a different score, and then you no longer have 4 levels, you actually have 3 levels, and they're all different scores relative to a control. But that's also, I should preface this, that is not in a different group study. So those are all things, I used to do EEG research, and all of that is within subjects. So all 30 of my subjects would have experienced all 4 conditions. So this was, think back to like paired samples t-tests, where you have multiple measures. So that's why I can subtract the control group out, because each person is contributing a control score and an experimental score, right? So it's the same person. Doing that for a between subjects design is not ideal, because you're adding in variability across groups, and that subtraction isn't coming from the same person. If that makes sense. Sorry, got a little off track there, but I don't want to give you bad experimental advice. So if you're doing within subjects, then you can create those different scores. But yeah, go ahead.
Yeah, so my question, if I'm like understanding this correctly, contrast is just separating like the variance of each into like an experimental group and a control group, and then separating your experimental groups again into like the specific.
Yes, exactly. It is a
How
very
many ever
drill
how
down.
groups you have?
Yes, it is
So-
very much a drill down approach, where you start with a lot of variance, and then you're partitioning your variance down into groups and comparing that partitioning over and over again.
Okay, so this is the concept, but the code, the coding will cover now, right?
Yeah, in just a second, we'll get to that. Yeah, so this is just the concept of what R is doing behind the scenes. But what the coding part will just require you to set up the data in a certain way. And so the coding part is, this is often called contrast coding. And so generally we do this with positive and negative numbers. So usually 0s, 1s, and 2s. So your first rule is that you want your sum, or I guess your second rule, I always say this is the first rule, things should add up to 0. So within a contrast, all your contrast coding should add up to 0. Your groups coded with your positive weights are going to be compared with the groups coded with negative weights. So right here in this dummy variable 1, this is actually contrast 1. So that giving placebo a -2 means placebo is going to be compared to low and high, and low and high are given the same value. So that means they're going to be averaged together. So they're going to get a weight of 1, placebo gets a weight of -2. Often you'll also see this done with a -1 and positive 0.5, positive 0.5, because each is contributing half, right? And then the other one is, but mathematically it's identical. And then for the second one, so this was that first placebo compared to drug. And then for the second contrast, okay, we've already compared placebo, so it automatically gets a 0 for our second contrast. We're just going to compare low to high. So compare -1 to +1. So you see how these all sum to 0 also. And then once you feed that information into the linear model function for R, then it'll calculate that as part of the model, these contrasts, these specific contrasts. All right, and so here are all these, they're actually already built-in functions in R that will create these contrasts for the contrast coding scheme itself for you, depending on what you want to do. Often, because I use this so rarely, in all honesty, if I'm doing contrast, it's at more of this simple level where I will just code it myself, like -2, 1, 1, and 0, because that's easy enough to do. But if you have something more complex, you can use these, like contrast Helmholtz, for example, is going to create a contrast code scheme for your second level with the first, and then the third with the first two. So it'll do your second level, your variable compared to the first level variable, and then the third level compared to the average of the first two levels. But to me, it gets more complicated because then I have to keep track of which variable is which. And I would rather just code it myself, but here are all these built-in functions to do this. All right, and essentially what you're going to get out, and what we'll look over in just a second whenever we get into R, is this sort of, again, because it's regression based, this is all, we're going to do this using the linear model. This is just like what we were doing to calculate the ANOVA using the LN statement. But before you run this, we're going to run some sort of contrast coding scheme, or we'll code it ourselves, depending. And then you're going to get out, and your linear model here is also going to give you your two contrasts here. So here you can see this is the mean of the group, the mean of the first two levels minus the first level, because that's what the Helmholtz does, and then mean of all three levels minus the mean of the two. So again, I think that's more confusing than just coding it ourselves here. So those are just the means. And then it also gives you out our coefficients, just like we got in before. And then it also gives you out the contrast coding, or actually this is what the variable will look like in this contrast coding scheme. So I think this will make a lot more sense once we get into R showing it. And I also think it makes more sense whenever you start labeling things. So whenever you label here, you can see we've actually added in these labels. Then your output right here just says what the contrast is itself. So then you're at this point, now you're just looking over for the specific p-value associated with that contrast. But this is the same thing as dose 1 and dose 2. It just is more, I think it's more intuitive if you add labels to your contrast, you can sort of keep track of what you're measuring, particularly because sometimes you're measuring the average of two conditions versus one condition. And to me, that gets more confusing to keep up with.
Aren't those p values like pretty extreme? In like,
Yes, these are very, very small. So
Right.
yes, they are, but it's because the data is made up, and I made it. I think I did this last year, but I'm pretty sure I made this data up to be different, even with a small n. So I made it. So if you have a huge effect, then you're going to have a really, really small p-value, because I made it have a very large mean differences, which you can also see here if you look in your. So these are the, where did that go? The mean differences. So mean of all minus the mean of the two. So this is a mean difference. Here are the mean differences. So. All right. But yes, you're right. These are very extreme. Usually, unless you have very large effects, you don't see this, particularly with small sample sizes, but this is fake data. So. Okay, so contrast coding, if you just do it without using that contrast dot Helmholtz or contrast dot Poly, I think was the other one. There are a bunch of different ways to do this. The other thing is you can just give it a vector of numbers. I think that's way easier, because to me, it is a lot more cognitive effort for me to keep track of what each of these contrast functions are doing and calling the right one than to just pass along the contrast weights. And then when you give it the weights yourself, then you know that you've weighted things appropriately. So we know our variables are in the order of placebo, low, and high. So I'm giving this -2, 1, and 1. So this is going to compare these two together to this one, right? Because it compares negative to positive. And I want these two to have the same weight because they're being averaged together. And then we're going to compare low to high, placebo, low, and high. So we're going to do 0 because we've already used placebo. We don't want that one to be even be considered here. And then low gets negative, high gets a positive. It will directly compare those two. All right. And then you can see this is essentially what it looks like in the R code whenever we get that out. So I'm going to hop into R and actually show you guys how to do this. If I can switch my screen share over. Okay. You guys see my R there? All right. So before we get into that really quickly, I just wanted to mention one other thing about ANOVA that I forgot to mention before we got into our contrast and follow-up tests. So ANOVA is very similar to t-test. In fact, it is if you have 2 levels and you're doing an ANOVA, then you're actually just doing a t-test on the F distribution. So I mentioned this before, the F distribution is just the square of the t-value. And so you can actually test this if we load in that GRE data set. So this is you should already have this stuff programmed in. So if we just looked at our GRE, no prep versus in class. So let's pretend there is no online. Let's just look at the no prep and in class. If we did a t-test of these, where this would be GRE, let's just do it on I think it was on the verbal scores that I did this on. And let's give it how we're going to group this. It should be GRE1, sorry. Score, there we go. Remember, we're going to assume that we have equal variances. So assume that we have our not violated. Oh no. Let's see what's happened here. Oh. So this should be the formula method. So here we can see this is our standard t-test, right? But remember, if I do this in ANOVA, so let's just use the base R AOV function, and I do the exact same thing. GRE1 score prep.
So you know the warning message that you got earlier, error in var y calling var x and factor x is defunct. That's the same one that I'm getting.
Okay, so I got this when what was I doing? Oh, because you need the tilde.
Oh, tilde, got it, instead of a comma.
Yeah, because it's stack data.
Got it.
So you can see here, this gives us the same results every time. So I'm just gonna grab this here, the same formula. So you can see doing 3 different methods. Look at what our p-value is every time, 2.18, 2.18, 2.18, right? And that was even with the t-test because we only have 2 levels. So whenever you're doing, if you're only doing 2 levels, you can just do a t-test. You don't have to do an ANOVA. But an ANOVA is a t-test at 2 level. If you have 2 levels, then that actually is an ANOVA. The only difference is this value is just the square root of your F. So if I took this F value and I took the square root of this, 1.23, and you can see up here, 1.23. Whoops, where'd it go? 1.23. Because the T value, the F distribution is just the square of the T distribution. So these, but you can only show this whenever you have two levels. Why? Why can't I show you this exact same thing if I have three levels?
T-test only compares to,
Exactly. T-test only compares two levels and ANOVA can compare more, but an ANOVA can compare two levels. It's just a T-test. But an ANOVA can also do three levels or more, right? Because an ANOVA then is going to say, okay, is there at least one difference among all these levels? All right, and so then we started talking about our effect size. So this leads me to effect size for R squared. So with a t-test, we've always talked about effect size in terms of Cohen's d, but R squared is also a measure that you can do this for. This is the formula for calculating R squared for a t-test. So I know this is a lot, but it's basically squaring the t, which remember this is essentially just your F score, and then divided by the t squared plus degrees of freedom. So if I just took this, oh, I have it right here, actually. If I just do this GRE t-test, so you can always, we always print these to the console, but you can actually put them in a variable form. And when you do that, then you can create variables out of these things. So GRE t-test, if we do the $sign and a tab, you can see all the all the values that are in that list that we just created. So I actually want the test statistic. So you can see that's my t value here. And you can also grab your degrees of freedom. I think this might be parameter. Let's make sure. Yep, parameter. Oh no, I just ran the whole thing. That's not what I wanted to do at all. All right. So DF here, and then you can see this is our R squared value. If you compare this back to our ANOVA, this gives you, oh, or our LN, this gives you the exact same R squared here. So do you see this 1543? That's the same value as this 1543. Because again, we just did an ANOVA on two levels. R squared is just the proportion of variance accounted for by your model. So remember, it's sums of squares model divided by sums of squares total. So for an F test, you don't actually have to manually calculate this R squared value because it automatically spits it out. But if you needed to, you could always, you know, put your ANOVA model here. Let's call this AOV, or we'll call it ANOVA. Call it ANOVA GRE. How about that? Then if you have your ANOVA GRE here, we can. Sorry, having an issue here with my parentheses. So now if you can make this into its own variable as well, and you can just pull the R squared directly from this. If you want, let's say if you needed to make calculate something else out of that. All right, so R squared, and remember this is the same thing as eta squared. It's just calling it a different thing. So now on to our follow-up tests. So let's go back to this sleep data that we have. So your all data should still be loaded. I'm just going to test to make sure it still is in mine. So we have our sleep and our dose. So let's say that we ran our ANOVA. I'm just going to do this this way. I usually use the AOV if I just want to see the table the fastest. Where we have our sleep dose, it should be a tilde dose data equals all. So here we have a significant ANOVA. So the next thing we're going to do our follow-up test. If we do no corrections, which again, you would not do that, you can see none. here, you can see which ones are significant, which comparisons. For comparison.
Between high and placebo.
Exactly. So between high and placebo here, this one is a significant effect. Low is not, or low and placebo is not, and high and low is almost, but not quite, right? But that was with no multiple correction. So if we want to do, so I usually do like FDR. Now we can see this is corrected for multiple comparisons. You can see what happened. Our p-values got a little bit bigger, but this one still stayed significant. So it survived. A lot of times you'll hear people say, oh, it doesn't survive correction, or it does survive correction. That means our p-value is still significant even after we applied a multiple comparisons correction, which is a good thing because that's how you have to report it. You can't report uncorrected values traditionally. You see our low got even further away from that threshold. So if we hadn't corrected, you might be tempted to say, oh, it's approaching significance, it's trending, but after you do correction, you can see that it's not even really that close, right? So we're up to like almost a 0.10 p-value at this point. And then you can also see here, if we change this to Bonferroni, that this is much more strict. See, every time. This is, if you get this error, it's because you didn't spell something right, because I do it every single time. I can never remember exactly how it wants it. So here you can see our high actually still stayed at the similar level with the FDR correction, but look at our low. This is how much it went. It made that go from uncorrected 0.06 all the way up to Bonferroni corrected 0.19. So it's quite far away from 0.05. So you can sort of see the strictness if you want to like play around with the different methods just to see like which ones are more strict and which ones are more liberal.
I have a question.
Yeah.
After the FDR corrections, you still have no correction. Oh, yeah. Oh, sorry. And the FDR is which one? Was it the Tukey?
FDR is the it's the Brock, this one that I can never remember. It's a false discovery rate is what FDR stands for.
Oh, I can't see the Tukey one in this list. So which one?
The Tukey one is not in this one. So we actually have to use this one down here. We have to use the library. Yep. So if you load this desk tools library, and then we do post hoc test, and then you put in your ANOVA test just like you would do before. Let's see, all dose. And now I'm going to put method equals, and then you can put whatever method you want. And here for Tukey's, it's HSD for honestly significant difference. And then here, now you can see low versus placebo, high versus placebo, high versus low. And again, generally these tests should agree with each other. So they are going to give you slightly different p-values each time. But in general, whenever you're looking at these tests, they're just different ways of correcting. So you can see the overall conclusion is the same across these different tests. Even though the p-value is slightly different, we're still concluding the difference is here, and that's in nowhere else.
And that's for strong effect, right? Because if it was close, then the Bonferroni, for example, might have been not significant.
Exactly. Yeah. And so, yeah. So if it's because this is a stronger effect, and it already was starting with a pretty low p-value at the corrections aren't raising it enough to be above our threshold. But yeah, if it was a smaller effect, so if your effect was already like 0.04, and the Bonferroni is going to wipe that out immediately. So that's not going to be significant, but it might still survive like a Tukey's HSD or an FDR correction. All right, so any questions about that? So, and you can look at the this post hoc test that it takes other methods other than the Tukey's honestly significant difference. If you ever are interested, you can just do help with the name of the library or the function that you're trying to find, and then this will pop up over here in the help window. And you can see down here, We have HSD, Bonferroni, LSD, Chef A. And also in these post hoc tests, you can also change your default alpha level. Almost never are you going to change it from 0.05 unless you're specifically doing something where you want to start with like a 0.01 or something like that. Or if you're, in a more liberal field where maybe the default value is like 0.1, maybe. I know in some marketing stuff, they tend to get a little bit more liberal with their p-values. So, maybe something like that. But yeah, you can actually change some of these parameters down here. And this will show you all the words that are the keywords that you need to use to pull different tests. All right, so let's go down to our stress data set. So if we want to load that in, and then we'll do some of these other follow-up tests as well as the planned contrast in the last 30 minutes that I have here. So I'm going to rename this all, which is bad programming. Don't generally do this because I already had a variable name all. So this is how mistakes happen, but here we are. So I'm going to change this. I think this is the exact same data set, but I just want to be sure. It might not be. Oh no, I think this one is different. All right, so we have our placebo low and high for our all, and we have our stress now and dose. That's why it's different. This is stress, not sleep. So very first thing we're going to do is let's see if we have significant differences. So I'm just going to call this ANOVA. Again, remember we can do it with AOV or the LM function. Doesn't really matter. I'm going to do the LM function this time. So we're going to say all stress, DV, dependent variable always goes first. And then dose. And then, so remember, this is just creating, whoops. LM is the function there. So this is just creating the object called ANOVA LM. So if I just type this down in the console, what you'll see is just this. So that we need the summary statement around that in order to actually get out a table of some sort. So now here you can see, this gives us the regression-based summary statement. I'm actually going to do this options siphon, so everything's not in scientific notation anymore. All right, so here you can see this is in our regression based. So we have our intercept with our estimates, our t-values, and then down here are our F statistics and p-values. If we wanted to see this as an ANOVA table, remember we use this from the CAR library, ANOVA LM. And again, this is going to put it in that more sums of squares, degrees of freedom, F value, the table that we've been working with. So based on these, do we have a significant F test? So we can look at the ANOVA table here, or we can even look at this from the LM summary. Yes, we do have a significant F test. Okay, so I think someone replied in the chat. Okay, so we do have a significant F test. So now let's say that we had actually already planned. So let's say we don't want to see all possible.
Sorry, which I guess I got out of the package. Which package has the ANOVA? Because it's not letting me.
CAR, it's the CAR package, CA.
Oh, okay. Okay, great. Thank you.
Yep. Okay, so yes, we have a significant F test. Let's say that we already have contrast plan that we wanted to do. I'm actually going to skip over this Helmholtz thing because I just don't. We can come back to it if we have time. Let's stick to the example that makes the most sense for this placebo low and high, right? So we're going to compare first placebo to drug. So we're going to say the control condition versus the collapsed low and high drug. And then our second contrast will be comparing directly the low and high. So the very first thing that we're going to do is just create this vector called C experimental versus control. of the contrast weights. So we have to remember, you always want to remember what order your factor is in. So the very first thing I'm going to do is do STR for structure. Remember, this is if you want to look at the structure of your data frame. What is this called? All. And I can see down here, dose factor with 3 levels, placebo low. So now that I know what order they're in, because the order matters, because that's the order these go in. Placebo, low, high. So if your factors are in different orders, then you would have to move these numbers around. So if they were listed as low, high, placebo, for example, but they're in this order, placebo, low, high. So we're going to do -2, 1, and 1. So this is going to compare this one to the combination of these two, low and high. Then our second contrast, we're just going to directly compare low and high. So -1 times 1, or -1 and 1. So low versus high. Placebo gets a 0. Why does placebo get a 0?
You're not testing it, right?
Exactly. We're not comparing this one. We already compared it up here. We're not interested in it anymore. So remember that just drill down graphic on the PowerPoint. So I'm going to create those. And if we look at these are just vectors of numbers, right? So that's very simple things that we've worked with before. Now this is something new. So we're going to say contrast all dose. So right now, if I just ran this part, if I looked at the contrasts that are in this data frame for dose, it's going to say this is the standard that it goes into whenever you first do the, oh no, it's not actually, hang on. I'm actually going to, I just want to reload this in and make sure this is right, since I ran it earlier. Yes, okay, yes, that is right. So this is the standard that it's going to test, where it defaults zeros here for the low, for the placebo, and then comparing the low, and then down here it'll compare the high. So we're going to change these contrasts to be these numbers, right? And so this is for the low. This is comparing low to nothing, high to itself. So if we do this C-bind, remember this just puts these into columns. So we're setting those contrasts to be the contrast that we set up. So now if we look at all dose, we can see it now has this attribute called contrasts. And here's the first one, -2, 1, and 1. Here's the second one, 0, -1, and 1. So we've just changed that. If we had 3 contrasts, it would add another column out here. And we would have put another column over here. So now that this is just all part of the data frame, right? And so if I do this structure again, you'll see this down here. Now look at dose. Not only is it a factor, but now it has this extra line, contrast, and then it has that information in it. So this is just giving us information about the variable here. All right, so now we're going to create the model. So I'm just using the AOV, but again, it gives us the exact same input as the LM. And then we're going to summarize it. And then I'm also going to use this split down here. You don't have to use this at all. So actually I can just show you what it'll do, but I'm doing this split list and naming scheme so that it will name the variables so that all of this. So this is giving this labels for each contrast. So placebo versus drug is 1, low versus high is 2. You don't have to do this whole like name scheme, all these extra name parts in it. You can just do the split equals list dose. But okay, so now what we see down here, we have dose, our usual, what we already found, ANOVA, and now placebo versus drug. We can see this contrast, and low versus high. You can see this contrast. Does this make sense? So we can
What is
also,
the
oh, go ahead.
dose p-value for the
Over.
dose p-value?
These p-values. Here's the
Well-
overall ANOVA, here's contrast
Oh,
1.
that's the overall ANOVA.
Yeah, and here's contrast 2. So they're all, so the overall ANOVA is significant. Contrast 1 is significant and contrast 2 is significant.
But we have Helmut as 3. So what does that mean?
So this is the Helmholtz up here. I didn't do this one because this one
Oh
automatically,
yeah.
and you can do it. It automatically creates the contrast coding for you, but it does it in a
Oh.
way where it will compare first 2 to 1, and then it compares 3 to the average of 1 and 2. And because of the way our data is set up, that would actually compare high to the average of placebo and low. So we would have to reorder our factors in order to use this contrast Helmholtz. So I skipped it. But if your data is set up that way, you can do that. And 3 is the number of levels that you have. So we have
Oh.
placebo, low, and high.
Yeah, but I don't think we would ever want to like because that we have 3 independent columns because we have those 3 independent groups. Do you think we would ever? I don't think I would ever have this situation where I would want to like compare the contrast of 2 columns average with 1. I would always be like 1:2, 2:1,
Yeah.
or like 2:3. So
And so for
I
most,
don't know.
yeah, I agree. Yeah, I definitely agree. Same here. And so for most of mine, if you want to specifically look at 1 to 2, 2 to 3, 1 to 3, then none of these contrasts will be helpful. Then you should stick to the up here, these post hoc tests and these pairwise with the p-adjust method. So depending on how your experiment is set up and what you're doing. So.
Allison, when you're doing these contrast tests, once you've done one level on its own, comparing it to others, is that level kind of burnt? You can't test it individually again?
Yeah, that's generally the statistical rules, is once you've done the contrast coding, once you've used one in isolation, you're not supposed to then use it again in isolate. So you can use placebo compared to the combination of some, and then you can use it, you can further split those combinations, but you can't keep pulling it down, I guess. So yeah, it's going to be very specific to if you have very specific hypotheses, and it's set up more for this like experimental versus control setup. And also if you, I don't know if you guys saw on the syllabus, there's a recommended book for R coding. I don't think I required it, but it's the one, I forget the guy's name off the top of my head, but he goes into a lot of detail about all of this contrast coding stuff. So like there's a lot of information about that, and even within R and how R is doing that. So if you want to learn more details about that, but yeah, but it's more, I think it's more limited but that's from my experience, because my experience is usually with wanting to compare all possible levels. So I guess it depends on what your research is doing.
It's by Andy Field and
Yes.
Jeremy Miles.
Yes, that one. So the field textbook, if you, because I think I just did like a recommended for it, that you don't have to actually get it. But he goes into a lot of detail with this. All right, so same thing, you can also do this with the LM statement as well. So for example, I'm going to show you here. Sorry, I lost my place here. Okay, so if I did summary.lm, summary.lm is also another option that you have. So I'm actually going to do this. I'm just going to grab this here. Okay. And so here now you can see this is the regression based view of doing this exact same thing, but you can see you still get your F statistic, your degrees of freedom, your p-value, and then now up here, instead of all these being your parameter estimates and your t-values associated with the intercept and the beta 1, beta 2, which this is why I don't go into too much into this, because we haven't really talked about regression that much, but we'll get to that towards the end. But this changes these to now be relative to the contrast coding that you put in. So now you can see your dose experimental versus control is this p-value, your dose low versus high, it's this p-value. You can again see overall conclusion is still going to be the same. Okay. All right. Okay, so are there any questions about this other than just general? It's really hard to do with contrast coding because I feel like a lot of this is so specific to your specific experiment. So I tend to err on the side of just teaching you guys how to test all possible outcomes, but I think it's important to know because in some labs that is what you have to do. So it's a good thing to know, but it really is so dependent on the experiments that you guys are doing because I don't know what's going to be a logical contrast for your own experiment. Like only you would know that and like how to sort of drill that down and how your experiments are set up. But it does help with the multiple comparisons problem. So good side for that. All right, so if there are no other questions about that, let me just make sure I've got everything on this PowerPoint. I think the very last thing that I wanted to mention were the assumptions, which I already briefly talked about these, but these are not new. This is because remember the ANOVA is building on the independent samples t-test. So we're still going to have normality assumptions. So we still want your residuals to be normally distributed. We want the scores within groups ideally to be normally distributed. So obviously if you plot all of your scores, so if you have 3 groups and you plot them all together on the same histogram, you're probably not going to get a normal distribution because you're expecting differences, right? You have them in 3 groups, they're probably different. So you want to check the distributions within the groups. Homogeneity of variance, you want to check, this is just like with independent samples t-test, check that the variances in the groups are roughly equal. If you violate homogeneity of variance, there are again corrections for this. That's going to do the same thing that we did with the independent samples t-test. It's going to alter your degrees of freedom, therefore making your F critical higher and making it more difficult to get significance, right? So this is going to penalize you a bit for your violation of homogeneity of variance. And so if they are unequal, I know we talked about in the independent samples t-test, we could do the Welch's t-test if you violated homogeneity of variance. There's also a Welch's F test. You can do that. It's actually more preferred, but you can also do something called a Brown-Forsyth F test. I tend to default to the Welch's F if violating that assumption. And then finally, independence of errors across the independent variable. So again, independence, you're going to see this pop up for assumptions over and over again, because we want to know that our observations are random and independent samples from the populations. And this is going to go back to a methodological problem. You want to make sure that the people in your placebo group were not also in your low drug dose group, right? Because now you're no longer, think about how we partitioned out that variance. We were comparing between versus within groups, that if one person popped up in multiple groups, now that's a problem because now that assumption isn't there. So that is a major problem. And you can't really fix this with stats. This is a methodological thing. So just, taking care of whenever you're collecting data and designing your experiment. It's relatively robust to violations of independence, but with group sizes are equal. So I think someone asked about this at the beginning of class, if you have different ends in your data. So if you have relatively equal, if you have equal group sizes among your 3 or however many groups that you have, usually violating these assumptions, you can just apply the, degrees of freedom corrections and carry on with your life. But if you have vastly different degrees or vastly different group sizes, so if you have one group that has 10 subjects and another group that has, like 30, 40 subjects, and you violated these assumptions, now you've got bigger problems because now correcting for this is much more difficult to correct for because of this. Because if you thinking about if your group sizes are that unequal, it is likely that you will violate some of these assumptions, but also if they're unequal now, whenever you're thinking back to the calculations, whenever you're calculating the contribution of variance and they're each contributing differently, now you're going to have more problems. So it's easier if you just keep things balanced as best as possible, and also just good for experimental design purposes. All right, and so whenever you do violate assumptions, again, there are corrections. If you violate normality, you can look into like transforming your data. And then worst case scenario, if you just have, you know, unsalvageable, I guess, data where you're just like I violated all these assumptions, like I have unequal samples, I have a lot of issues, then that's when you start going into the non-parametric test route, where there are a wider variety of tests that don't depend on all these very core assumptions. All right, and so I'm not actually going to go through each of these just for time purposes, because we already went through these with independent sample t-tests, and these are all going to be the same. You want normality within groups, you want your homogeneity of variance, you want your independence of samples, all of this. So, and then your testing it is going to be, oh, maybe actually I will show you this one thing in R, and then I'll wrap up. So because we talked about our QQ plots, remember for our independent samples t-test, where we just did the QQ plot was the function. If you actually plot the ANOVA model that you create, like with AOV, you can plot out both the QQ plot and the residual values. So let me just go over there really quickly to show you that. So if we have our, so I'm gonna have this, our stress model here. And then remember we have our ANOVA, gives you stress model. Oh, no, it's not what we want. There we go. And then if you just do plot stress model, now over here in our plot window, we should have it. Oh, there you go. So you can see as you have to hit return, and it'll actually plot through all of these plots here. So you can see here, you have your residuals, and it already splits across your different factor levels. This is actually very convenient. So you don't have to go in and manually, pull out your placebo, pull out your low, pull out your high. You can just look at these, look at your standardized residuals. So see, these look pretty good. They're relatively normally distributed. You can see this QQ plot. So do you remember how we talked about that line, how they should sort of fall along that line? So these, again, looking pretty good. And your residuals versus your fitted in the model, again, these are looking pretty good. Like they're relatively normally distributed. We're back to here. But again, you can do this after. So technically you're supposed to look at your data before, you do all your modeling, but this is very helpful for looking at the residuals and seeing if you violated anything. Okay, so are there any questions about that? About assumptions, effect size, contrast coding, post hoc tests? Any of that? All right, so if
Not